Starting preview, it says. Come on, guys, get the camera going. Hopefully, let me check. Do a refresh. I still don't see anything. Why is this live? It says live now. Okay, hopefully. Hopefully we're live. I'm thinking we're live. Yes, I see it there. Fantastic. Okay, it should be public. I want to make sure everybody can see this. Let's see if there are more than 34 watching now. That's good. Okay, I think we're good. Thanks, you guys. I'm a little bit late today. I had a few technical issues. There always seems to be something technical when I start these things. So I appreciate you kind of bearing with me while I get it done. This is going to be an amazing talk. I'm very excited about this particular class, not just because it's the first of a series of courses on solar phenomena and space weather phenomena in general, but because this is one that's near and dear to my heart. This is coronal mass ejections. And believe it or not, a lot of people think I'm a solar physicist, and for those who don't know me, I'll tell you I'm not a solar physicist. My training is actually in what's called space plasma physics. Now, space plasma is essentially everything from the sun's corona on out to the Earth or on out to whatever planet somebody happens to be studying within our heliosphere, within the sun's influence. And that's really where I've always lived. That was where I did my thesis and all of the work that I did as a graduate student, even a little bit as an undergraduate. I, believe it or not, didn't study the sun so much. So a lot of this is very exciting and fun for me because it allows me to go back and take a look at some of the stuff that, that I had learned but had forgotten, or I had learned only partially because I only learned what I needed to learn. And I got to go back and look at the history. And just to give you a little bit of insight into how this course developed, when I was chatting with everybody on Patreon about doing these particular courses on just all the different phenomena, because there's so many different ways that we can get confused about, what is a solar flare compared to a coronal mass ejection, and what is what is a radiation storm, these energetic particles that come off the sun, and how do you tell the difference, and how do they affect Earth, and why am I always so confused about it? Because everybody uses all these words interchangeably. And when I went back and decided, okay, let's just break it down into each little phenomena, I started realizing that with coronal mass ejections, that really, in order to kind of understand why we call them what we call them, why we describe them the way we have, you really had to take a look at the history of how they were discovered, because it really was one of these things where, and a lot of solar science is this way, where it really is observation driven. That if you can't see something, you don't know what's happening, and you have no idea what it is that's causing it. So really, your understanding then of a particular phenomena unfolds based on what you can observe. And so the history became very much folded into the whole context of what coronal mass ejections are, and how our view of what they are today seems a little bit different than maybe the way we had always viewed them, or really a lot of times they look different than the way our standard models have described them. And the funny thing is, if we had started with a totally different set of instrumentation, and I think you'll understand this as the talk goes on, that if we had started off with a totally different kind of instrumentation, we may not have labeled the things that we label when it comes to these structures. We may not have considered things like a loop, a cavity, and a core. We may not have considered that kind of definition at all. We may have started off with something completely different. And so you'll see that the discovery of these structures was very piecewise. And so as I continued to put this together, the longer it got, I went, oh God, I'm not going to get a chance to go into all the solar wind stuff and all of the stuff that really is my bailiwick when I did all my graduate work. So that's actually going to have to wait for a second course. So this CME course, in a sense, has got to be a two-parter, which is probably wise anyway, because the solar flare one will likely be a two-parter as well, because we'll talk about solar flares as they have been observed on the sun and as they erupt. But then we'll also talk about things like solar energetic particles, which become far more important and far more interesting really out in the heliosphere, out as they're traveling through space to Earth or to some other planet. So in that sense, I guess these things are kind of, all of these phenomena are kind of a two-part experience. You've got what happens at the sun, and then there's a whole other world that evolves and opens up once you get away from the sun and you go out into the solar wind. So hopefully that gives anybody who got my early description of what this course was going to be about, and I mentioned that it was going to have the solar wind aspect to it. Hopefully you can understand now why I'm kind of saving that for later, because otherwise, I mean, I already have 30 charts or more in this course, and if I were to try to continue on, I mean, we'd be here for 4 hours and you guys would be, you know, screaming at me to stop. enough already, enough. So that's why I've kind of broken it down. And as always, I want to thank all my patrons here. These are the ones that are sponsoring the mini courses. You can see them here. Hopefully they don't mind me showing their names, but my hat's off to you. You all have created such a wonderful discussion on Patreon, and I couldn't do this without you. And then also my steering committee. These are the people that I get together with once a month who really kind of talk about, what we talk about is where where these courses should go, where the whole effort should go. They kind of help keep me grounded in some of the new research that's being done in various areas outside of my typical scientific and academic community. And so ham radio, so in Aurora, so in medical research, areas that are just beyond the normal beaten path. And I'm just so incredibly grateful for them, because they just opened whole new worlds to me. And I'm looking very forward to, I'm actually going to be meeting with them this upcoming week, so we have a lot of good stuff to talk about. Anyway, let me take a look really fast at the chat and see what you guys are saying. Thanks for, okay, 53. Oh, good. I'm looks like I'm loud and clear. Good. Yes. We are getting very we are getting some very interesting solar activity right now. We have a region that has been popping some C-class flares, so that's actually boosted the solar flux right now into the mid-70s. It's a balmy 75, maybe even higher right now. And that's fantastic for amateur radio and shortwave radio responders. The day side should be wonderful. You're probably getting a little bit of noise on the bands right now, simply because every now and again you're getting these solar flares. And some of them are gradual. So I've been busy with this, but I've been kind of keeping one eye on the sun, just to see whether or not we're going to get an eruption that will actually launch one of these coronal mass ejections at us. Don't know. It doesn't look like anything yet, but I haven't been able to pay super close attention. But I'll definitely let you know. And it looks like we're getting primed to have another flare here very shortly, because I'm watching that X-ray flux really ramp up. And it usually does that. You get a lot of boost in the X-ray flux right before something goes off. So we'll see. I don't know if we're going to get an M-class flare, but we've gotten a C5, which for right now is pretty impressive. So we'll see. But we are keeping our eyes on that. But yes, amateur radio operators, enjoy the daytime right now. We're getting some decent, you should be getting some decent propagation on the bands. Okay, let's see. Anyone remember the old days when we used to get CMEs? Yes, I know, no kidding. Hi, Tamitha, are you familiar with the Dellard theory? I don't know. Not the name. Let's see. Anything to do with the incoming grand solar minimum? This course will not. This course will not go into that. I'm debating whether I should do that. If I do something like that and do a grand minimum course, I don't know. I might include it in something like a like the Earth's magnetic field flipping. I've been getting a lot of questions about that, especially with all the recent news about the poles moving. So I may do that, but it's going to be after we get through the solar the solar phenomena mini-series that we're doing here, because we've got probably 4 courses, maybe 5 total with this one, that are going to be bits and pieces of the solar phenomena. So you may have to wait a little bit for that, but that's a good one to come. Yes, and I will be talking about aliens. If believe it or not, it's going to be fun. It looks like I'm seeing you guys from all over. Hello to Brazil. Hello to the UK. Hello to, did someone say from Portugal, from Finland? Love it. I love it, guys. Thank you so much for coming on. I love seeing the South American folk as well. It's great to see you guys on because your space weather is so unique and you get hit by it so much. So let me begin without any further ado, yes? So what I've done is I wanted to kind of give you just a basic idea of what we are going to be through the set of mini courses that we're going to do, what we're going to be looking at. Today we are going to be talking about solar storms, aka coronal mass ejections. That's this guy right here. We are not going to be talking about solar flares so much. They are part of this discussion, and yes, you will see some of that, but I'm not going to go into the dynamics too much when it comes to solar flares. These two are oftentimes very associated with one another. You can have a solar flare and have a CME be launched at the same time. It very oftentimes happen together, but they don't have to. Like right now, for example, the active region that's on the Earth-facing sun that's popping flares, it's not launching these, not the last time I saw, even though we had something called a gradual flare. It looked like it could have, but it didn't. So you can have solar flares without coronal mass ejections, and yet you can also get coronal mass ejections without flares. And they're usually very slow eruptions, and those are, and even at the very far end of those, we call them stealth CMEs. That's something that Halo CME and I study quite a bit. These are structures that are so slow and so wispy that you don't even see them launch off the disk at all. So, and that's something I will talk about, not so much today. That gets more into the solar wind aspect. So I will probably pick up the CME discussion with stealth CMEs when it comes to the solar wind part of this set of series. Now, another thing that we deal with are solar radiation storms, also called solar energetic particles. That's the scientific jargon. I will probably, as long as I'm talking with you guys, I'll always refer to them as solar radiation storms, except in many courses like this. I might, you might hear me say the jargon, and I'll use them interchangeably because anymore it's become so habitual for me. It's like two languages. I just kind of use them together. And solar energetic particles can be launched by solar flares, by coronal mass ejections, well, they're driven by coronal mass ejections, and also by fast solar wind that come from these coronal holes. And again, I won't be talking about this, or this today, but these are the four main phenomena that affect Earth. The most beautiful, of course, are coronal mass ejections, and that's one of the reasons why it's so fun to talk about them. Okay, so because of that, and you will see this all throughout this talk, we talk about how do we view such a complex star when it comes to when we have so many different types of solar phenomena. Believe it or not, all of these pictures were taken essentially at the same time. Doesn't look like it, but they all really are just parts of this onion that we call the sun. The sun is, if you look at it as an onion, it's got all these different layers. And those of you who've watched my mini courses in the past, especially the ones with sunspots and telescopes, I went over some of this. We always have to worry about what type of phenomena we're seeing in what layer, essentially what part of the solar atmosphere or even on the surface. Like these are really, this is the surface in white light, you can see sunspots. If you go a little bit higher in temperature, you actually start seeing some of the plage regions and the electrical connectivity between the sunspots when there's solar flares. You go a little bit higher in temperature, now you're looking at a higher layer in the solar atmosphere. This is really the chromosphere region. This is where you start seeing coronal mass ejections, that into the corona. Go a little bit higher, now you're really beginning to see the corona, see all that wispy stuff coming off. This is the source of the solar wind. But believe it or not, here you don't see that coronal mass ejection at all, do you? But you see it here. And here you kind of see something, but not really. You don't really get a good view. Now we go a little bit higher in temperature, and now you're beginning to see magnetic field loops. Hopefully you can see that. And again, you can see a little bit of that coronal mass ejection. And then you go even hotter. Again, now you're seeing some of the hottest parts of like when you see active regions and flare loops and things. When that, you'll often see us talk about the blue sun. And you can see the hottest part of that coronal mass ejection right there. But we need all this stuff to be able to see all of the various types of phenomena that are occurring on the sun, and we just can't look at them by imaging one layer of the sun. So we have to use different imagery to see it. And because of this complexity, it really slowed our understanding of CMEs, and it took decades upon decades and mission after mission to be able to really figure out what they are and what they were doing to us. Some of our current understanding, I don't know if I even have these videos hooked up for you. Whoops. Is it stuck? Okay, let's see. Let's see if this video plays. Here is a classic solar flare, just so you can see it. 1, 2, 3, come on. There you go, boom. Hopefully you see that. And that's a classic solar flare, and you see it in, what you see, 131 angstroms. And that is part of the active sun. Here is a coronal mass ejection, so you can see the difference. See, with solar flares, they occur very, very quickly. They are basically just light bursts, and they can release X-rays and radio bursts, and they do give you solar energetic particle storms, so that means radiation storms. But they travel really quickly. Essentially, it takes about 8 minutes to reach Earth, and these are what cause radio blackouts. And they happen very, very, very fast. But coronal mass ejections, on the other hand, are very different. They're much slower, much more massive. This isn't just light. This is actually loops of material. Just so, I mean, an absolute ton of material comes out here. And you can see it in a loop because it's the magnetic field that carries it. Now I froze it there so you could see that loop, but here it is. Here's the sun again. Here's that loop now coming out into interplanetary space. This is 2 different coronagraphs, coronagraph views. This one goes out 15 Earth solar radii out, and you can see, I'm going to probably try to stop it right here. Hopefully you can still see that. Can you guys see that loop? Yeah, just barely, right? That is because that loop, as you saw, it's the same loop that you saw here. It's just expanding out. And the reason why it's a loop like that, you know what, I forgot my slinky. I keep doing that. I mean to bring my slinky in here, and I forget to. The reason for that is that this is actually a solar slinky. It's a slinky that has been attached to the sun, and as it expands out, it just gets bigger and bigger and bigger. This slinky is part of the sun's magnetic field that's kind of coiled up, and excuse me, and the phone just rang, so I'm got distracted. And it's kind of coiled up, and so what ends up happening is that the plasma, this material that is coming out of the sun, because it is charged, it sees that magnetic field, but it sees it as like a jail. And so anytime you have a gas that you have to charge, that you have to ionize, which is what happens on the sun, that gas then, because it's charged, it sees electric and magnetic fields. And anytime they are there, it's kind of confined around that particular field. So believe it or not, the particle just spins back and forth around the field that's constraining it. And if the field looks like a slinky, well, then the particles just go up and down around that field, and they're kind of jailed in this tube. And that's exactly what you're seeing here. You're actually seeing the center of this tube. If I had a slinky that came out and you looked, and I put it right like this, you're actually looking down the center, and what you're seeing are particles that are traveling up and down this tube around the edges, and that's why you're seeing this here. It's actually scattered light. You're not actually looking at, excuse me, you're not exactly looking at the magnetic field directly, but what you are seeing is light scattered, what we call Thomson scattering. It's from electrons that are traveling along this kind of invisible jail. And this will continue, this whole structure will continue to evolve and get larger and bend a little bit, but stay reasonably coherent all the way out to Earth. And thank God for that, because if it didn't, us scientists would have even a harder time trying to understand when, what happens to these structures and when they hit Earth, whether or not they can actually cause big solar storms. And the details of that, of course, are going to be what I'll go into in my second course that talks about the solar wind and how these structures evolve out in the solar wind. So you won't see me go past just coronagraphs today. That'll be as far out into space as I get. But the difference between these solar flare, remember these are 8 minutes to reach Earth. These take a lot longer. They go a lot more slowly. I know it seems silly to say that 1,500 kilometers a second is slow, but believe it or not, it is relative to the speed of light. So they travel to Earth in about 2 to 5 days. So when you see a solar flare, if a CME was launched with that solar flare, you have 2 to 5 days, depending upon how big it was, how fast it's moving. You have 2 to 5 days before you have a chance to get an actual solar storm at Earth, what we call a big geomagnetic storm. Now you can get radio blackouts and you can get solar radiation storms prior to that, because radio blackouts are just light. That's radio noise that travels at the speed of light, same as a flare. And then solar energetic particles, meaning radiation storms, those travel a little bit slower, but they take only about an hour to get to Earth. So you can get radiation storms and radio blackouts very fast from solar flares, but that CME, it's going to take a few days. Even the fastest ones still take about a day to get here. And the fastest ones are the Carrington class events that we just don't see very often, thank goodness. Anyway, so hopefully that kind of sets the stage a little bit. I'm going to show you really how far out we can view these coronal mass ejections. You can actually see, so here's a coronagraph. This is, again, that 15 Earth solar radii view out. That's an occulting disk. I'll talk about that more. So it basically creates a false eclipse, a fake eclipse. And you can see, look at that solar wind. Look at all that stuff being blown out. And pretty soon you're going to see, see all those little stars? You're going to see a blizzard hitting very, very soon. Boom! Right there. See that? That blizzard is a solar radiation storm. Those are solar energetic particle events. The sad thing about coronagraphs, as you can see right there, is that those blizzards blind coronagraphs. I mean, if you have a really bad one, you can't even see through it to see what might actually be going on underneath. So that's one of the bad things about coronagraphs. It still happens. This is SOHO. You still get blinded by solar radiation storms when they occur. That doesn't happen with every type of particle detector, imager, but it does happen a lot of the time. Here's one that goes out. This is the heliospheric imager on stereo. This thing images all the way out to 1 AU, so that's where the Earth is. So basically from the sun and the solar wind all the way out to Earth. And you can actually see, hopefully you can see some of these waves, some of these parts of the coronal mass ejection just scatter light all the way out here. So in some cases we actually can, and here's the same thing from the opposite direction. So in some cases we really can image these, look at that, image these things all the way out to Earth. The problem is that to get really good images of these things, oftentimes the imagery doesn't come faster than real time. So it's very hard to use these in a really excellent capacity for space weather forecasting. So that we can get beacon images, but for HI, we really need the science grade images to be able to really be able to see all the fine structure and get us to understand what might actually be hitting us. But we have used them to some degree in forecasting, and hopefully things will continue to get better. And I think I went through all of that. So this hopefully kind of sets the stage a little bit of what we're going to be looking at. Now I'm going to get into the history, and this is really where it gets fun, okay? Because we're just now going into how we ended up figuring out what coronal mass ejections were. So I'm just going to, if you ever get a chance to read A Brief History of CME Science, it was written by David Alexander, Ian Richardson, a good friend of mine, and Thomas Zurbuchen. You may recognize Tom's name from the fact that he is now the NASA Heliospheric Sciences Division Administrator, or Deputy Administrator, I believe. I can't remember his exact title. But we've always been so excited ever since he got to be promoted to that position, because we get a space weather expert in the executive branch of NASA. So we're extremely happy to have him there. But they wrote this really nice kind of historical review. And in it, they pulled out some of the very early ideas of what coronal mass ejections were. I mean, we're talking about people back in 1919. Linderman and back in 1919 and Chapman and Ferraro were looking at coronal mass ejections not from any clue that there were anything such as coronal mass ejections. But looking at Earth and seeing suddenly we'd get these huge storms, and their magnetometers on the ground that they had would just suddenly go crazy, and they had no idea why. And there'd be aurora that would come way down when all this stuff would happen. And there were just all these weird anomalies that would occur on the ground, and they could see it. They'd get it in their telegraph lines. They'd, like I said, the magnetometers would go nuts. They'd read, they'd just get all these weird things. And it caused Chapman and Ferraro in 1929 to start coming up with ideas that there must be these blobs that are hitting Earth and causing all of these current systems. And we actually still to this day talk about Chapman and Ferraro currents in the magnetosphere. But we had no idea at the time that there was anything like a solar wind. We just thought space was space. It was very empty. And just every now and again, the sun must be sending these little blobs at us and causing, when the blobs hit Earth, they would cause all these problems in the upper atmosphere and problems for our magnetic shield. I'm not even sure we understood at the time how our magnetic shield kind of expanded out into space. We really didn't even understand what shape our magnetic shield could have possibly taken out in space. We sure didn't call it a magnetosphere yet, but this was all the beginning of that. And then a little bit later, we started getting ideas that because it was all magnetism, and and we began to get ideas about the sun being an electromagnetic sphere, and that we had these plasma clouds that would actually be shot out somehow from the sun. And Alfvén began, looking at all sorts of things. As a matter of fact, we've got something called Alfvén waves that were named after him. Johannes Alfvén, in 1954, created one of the first ideas that we had particles that were frozen into the magnetic field, meaning the magnetic field jailed the particles. That's what we call frozen in flux. He actually talked about it from the other way around, that the field is frozen into the plasma, meaning the particles held the field in place. But either way you look at it, whether you look at it as the magnetic field jailing the particles or the particles locking the field into place, it's still the same kind of thing. You basically have magnetic field that cannot move without the particles moving, and the particles not being able to move without dragging the magnetic field with it. And it created a whole kind of world of I don't think we had started really MHD, magnetohydrodynamics yet, but we understood Maxwell's laws, and we began to realize that space was based in electromagnetism. So he drew a picture of these big blobs being shot out from the sun. But even with that, these big blobs that had plasma and magnetic field, and that's what hit Earth and caused these big geomagnetic storms. And it was interacting with the magnetic sphere that we had as a shield in place. And as we still were trying to get understanding of what the Earth's magnetosphere really looked like, we still didn't picture it as something that was being blown by a solar wind. So our views, and if you look at drawings of the Earth's magnetosphere back then, you didn't see any influence from a solar wind. We didn't know there was any. And then Parker, let's see where we have Parker. We have Parker coming out in 1961. I'm skipping ahead, sorry about that. So around the same time that we still didn't know there was solar wind, we had things like turbulent clouds. We had things like just completely stochastic things that were just big bubbles and tubes being kind of overlapping each other like a big set of big bowl of spaghetti being thrown at us. That was Morrison in '56. We had ideas of tongues. This was Cosidi in 1958. We had bottles and bubbles. That was Piddington in 1958. And then finally, in 1961, we had Eugene Parker, who's still with us today. And the Parker Solar Probe, right, was named after him. He came out with this radical idea that there's a solar wind, that the sun isn't just sending out these random blobs to us that hit Earth, and then Earth, shakes and rattles and causes has a geomagnetic storm. There's a wind that's hitting us all the time. And these structures are actually embedded in this wind. And if we wanted to understand really the real dynamics of what was happening, we were going to have to understand how these structures erupted and tore off the sun and became part of this solar wind expansion. Because Parker talked about this, the plasma that's constantly coming off of the sun, and it's expanding and participating in this, in this huge, just literally expansion that became the heliosphere. So, and that I can, once again, these are things, the details of this stuff I will get into the next course. It's not part of this one. I don't want to spend too much time on this. But it gives you an idea, looking at some of these kind of hilarious ideas, that back in the day, even just back in 1961, I bet you there's some people watching this Q&A who were born earlier than 1961. My husband was. So, you know, and I almost was, not quite. But, you know, this wasn't that long ago. I mean, this is in our lifetimes that we didn't even know we had a solar wind. So imagine how hard it is, just to set the stage, imagine how incredibly hard it must be to think of what a coronal mass ejection could possibly be, or what one of these solar storms must be, when you don't even realize there's a solar wind, right? I mean, it kind of blows the mind. And like I said, it wasn't that long ago that that's the way we thought. That was the prevailing idea. So the first observation of a coronal mass ejection was done, I don't know if you guys can read this, it's kind of fuzzy, but this is on a NASA mission called OSO-7. And it was a naval research, an NRL mission, and this was the Coronagraph that they flew. They wanted to create in space a false eclipse, and so they knew how to kind of how to do it, and so they flew this particular instrument, and sure enough, you get this corona. We've seen the coronas on the ground. We knew that if we created an eclipse, you know, we might see the same types of things that we see when the moon eclipses the sun. So obviously this seemed like you know, an ideal instrument to try to fly in space. So we knew we could study something. And sure enough, you see this vague corona, you see something begin to emerge. And you see this blob? No, we had no idea what it was we were watching. But there's something right there that had never been imagined before. So we kind of knew, okay, well, wait a minute. Maybe this is one of those things that the sun shoots off that hits Earth and causes these crazy storms. Maybe we actually could learn a bit more by looking at their structure. And so there were a lot of papers written, Tosi et al., if you ever want to look it up. There's an excellent paper by him that talks about this in various terms. It's actually kind of cute when you know what a CME looks like today and how we think of it today, to kind of go back in the historical record and see, you know, all of the excitement and buzz about this first observation, that we could actually catch some of these things that have before that were completely invisible. And then here's another one. This was in November 1975, I think. It's hard to see that, but I think it's 75. This was the first halo CME. So now the difference between just a regular coronal mass ejection seen by a coronagraph and a halo CME is that a halo CME is one that creates a halo around the occulting disk and actually comes outwards. See, you can see here. So follow it this way. Here's the evolution of it. And imagine being an early scientist going, well, what's the difference? Not necessarily knowing that a halo CME means that's something that's either coming at you or going away from you. It must have been, you know, an amazing thought to think, well, how many, you know, is this a storm that's actually going all the way around the sun? Is the sun launching something all the way around the disk? Or what are we seeing projection effects? This is where people began to really understand that we need to study these a lot more from a lot other angles than just something like this in order to really get an idea of what's going on. But pretty neat, huh? I mean, our original view of what these structures were was very fuzzy and really just something that was coming out of the corona from coronagraphs. Now, if I talk about the history of space-based coronagraphs for just a second, you can see here's OSO-7 launched in 1971. It lasted to 73, so I guess that must have been 1973 there. Because I don't think that was a Skylab picture, that halo CME. Maybe it was Skylab, but I think it was OSO-7. And here's the field of view that may not mean all that much to anyone. The field of view in solar radii. So from 3 to 10 solar radii here. Here, for example, is LASCO from 1.1 to 32 solar radii. So we were looking very early on, very close to the sun. Our coronagraphs really weren't all that sensitive to be able to pick up stuff further and further away from the sun, because the emission gets weaker and weaker and weaker as these coronal mass ejections continue to expand. Right? We need much more sensitive optics to be able to see that, and detectors to see it. So you get spatial resolution, and the key results of these particular ones, of course, you get with OSO 7. You had the first detection. In Skylab, we launched another coronagraph in Skylab. As a matter of fact, I wish I had pulled out the picture. I still have an actual physical film on photographic paper of one of the slowest CMEs ever recorded that was done on the Skylab coronagraph, and it looks like this really weird bubble, and it just kind of comes out. They said it was something like less than 200 kilometers a second, and Jack Gosling gave me that picture. I almost had him sign it because it was just such a cute thing. He had it just laying around his office, and anybody who knows Jack Gosling or has heard of him, he's a very, very famous space physicist, and he, unfortunately, he's no longer with us, but he was one of my thesis advisors at IGPP, and he taught me basically everything I know about bidirectional streaming of electrons and IC3 data and stuff like this. But he was one of the early pioneers of coronal mass ejection research, and he had probably forgotten more stuff than I've ever learned. That's how amazing he was. So, but at any rate, I still have that picture of the coronagraph image of a CME from Skylab, and any time I want to be humbled, I kind of look at that because it reminds me of how slow doing imagery back then was. They actually had to print the stuff on, it would have to be exposed on film, and then they'd have to develop the film, and then they'd get a picture. And you can think of how incredibly slow that is compared to digital cameras that we have today, or CCDs. It gives you an idea of how little we were able to do in terms of science and understanding the evolution of these structures if we actually had to take a picture, get it developed, and then see, and then take another picture, get it developed, and then see. It was a very, very slow and painful process. Then we had the solar wind chronograph. As you can see, and you can actually see here how many coronal mass ejections it was actually able to view. Here we started going from 30 to 100, now into the thousands. We were starting to get statistics, understanding the difference between regular ones and halos. We were beginning to resolve shocks. Then we had the SMM mission, and I'll show you some of the details of that. Also had thousands of images, and we started to understand the three-part structure, which formed part of our standard model. So as you can see here, with this stuff, this is really where we started understanding how coronal mass ejections worked, all from coronagraphs. We're not even talking on the disk images yet, and you'll see what a big role that played. Then we get SOHO LASCO. Now, you guys know SOHO, right? That thing was launched back in 1995, and this thing has taken way over 10,000 CMEs. We've gotten so much physics out of it, it's not even funny. You can't even begin to put a limit on the amount of science we've managed to get out of SOHO. And now we have Stereo SECI from 2006, and with, of course, Stereo A, it's current. Of course, Stereo B is, we don't know if it's completely gone yet, but it's been gone for some time. Many of the images are back-sided, so we can't say that we've always gotten early, or that we've always gotten Earth coverage from stereo. And we've had thousands of CMEs, like I said, backside dissection, stealth CMEs. That was something that we really didn't understand before stereo. It has been able to do, really get us to understand a large aspect of the, the whole zoo, let me say, of what CMEs are and what they can be, all the way up from very large to very, very narrow structures that we might have mistaken for streamers or something else. It's even helped us understand blobs that we don't even know if we can classify them as pure CMEs, but we've got, I think Alexis Rouillard has been looking at these for quite some time. So we have blobs that could be like little mini CMEs inside the current sheet itself from the sun. And it really tells us that the scale size of these things can go from very ginormous structures to very, very small ones. But I will say these are the only coronagraphs that we've had in space. And if there's one thing, if the stereo is the one that is, only sometimes looking at coronal mass ejections from the Earth's point of view, the only one that we actually have doing it all the time is SOHO SOHO LASCO, right? But it was launched in 1995. So do you see something strange about this? SOHO, if it was launched in 1995, it's 24 years old, okay? This spacecraft is not young. I don't know a single spacecraft that was ever designed to live 24 years. I mean, that's older than some of the people who are watching this Q&A, no doubt. And so I get a little bit, heartbroken when I hear people bag on SOHO, or I hear people bag on the SOHO instrument team because of stuff like this, right? This is SOHO. This is just to give you an idea of how long SOHO's been around. This is 1996. This was solar minimum. SOHO imaged this, all right, in EIT. Here we go through the first solar maximum around 2000 to 2002-ish, right? And then we come down to a solar minimum. And then we go back up to solar maximum again. And this is 2015, and we're already back down to a solar minimum. And SOHO's still around. That means SOHO has gone through 1, 2, and now into the third solar minimum, and it's seen 2 solar maxes. That's huge. For a spacecraft that was never intended to last that long, that's huge. Now, are there anomalies? Sure. Sure. Are these aliens? It looks like the door's not open. You got a lot of stray light. You got the occulter. This is part of the optics. You can see it sliding all over the place because they were moving something like a filter wheel inside. Oh, look, there it is again. Oh, look, lots of stray light. Oh, look, they may have been rotating the spacecraft. Oh, look, even more stray light. Does any of this look like it could be aliens? Or maybe SOHO needs testing. It needs testing. I'm waiting for the phone to stop. I may grab that phone and throw it outside. Hold on, let me get the phone. Babe, the phone. Sorry about that, guys. You probably heard that because my mic was on. All right, so here's the thing. Are we going to continue to see images like this? Sure, of course we are. Why? Well, we got keyhole maneuvers. Anybody ever heard of that? You can look up SOHO and go to keyhole maneuvers. There are times when SOHO it doesn't get telemetry. There are times when they're doing testing. There are times when we need to recalibrate something. There are times when we need to do instrument maintenance, CCD bakeouts. We need to roll the spacecraft. We need to change the instruments. We need to test things. We need to recalibrate things. Oh yeah, and by the way, we lost SOHO once. All of the gyroscopes on SOHO are dead. Gyroscopes are what spacecraft use to be able to maintain their equilibrium, right? Maintain their trajectory, maintain their stabilization. Gyroscopes are something that most spacecraft cannot fly without. And yet SOHO's been doing it for so long. And why? Because a very dedicated team of people, of scientists and engineers from all over the world busted their arses to save this spacecraft. And just because SOHO goes out and there are frames missing from the data, there are weird anomalies like this, there are times that you've got a CCD bakeout, the idea that all of this is because the scientists are working with Big Brother and are hiding something is ridiculous. SOHO is 24 years old, and the scientists have more blood, sweat, and tears up in that machine trying to make it work with baling wire and chewing gum than I would ever have believed possible. And instead of hiding, this team is celebrating. You want to know who the SOHO team is that saved this spacecraft? Here they are. You want to know their names? Look it up. It's in black and white right underneath this picture. They are not hiding. These are real life people, living, beautiful, wonderful scientists busting their ass to be able to give us CME science, because SOHO is the only spacecraft that has a coronagraph on it that stares at the sun from our Earth vantage point. It's the only one. They're not aliens, okay? They're people. So this is my tirade when it comes to SOHO. Now we'll see some more fun stuff later, but this is the one that really gets me, because there are so many people out there who rip on these scientists and rip on my colleagues who have busted their butts to give these other people the data that they use to do whatever, to make a living on YouTube off of this data. And yet every time they get a chance, they rip on these people as if they're evil. And that just breaks my heart. Okay? So please remember that the next time you see somebody say that this is an alien, or the scientists and the US government are trying to prevent us from seeing what's really happening out there. All right, enough. So let me see if anybody has any comments about that. Anybody have anything? Yeah, good. Thank you. I appreciate that. Very cool visual of SOHO's accomplishments. Thank you. Yeah, I wondered what aliens were going to turn up. Cute. Is there ever a chance of collecting material ejected from the sun? Boy, that's an interesting question. You know, it's so tenuous. I mean, my goodness. We're going to know a lot more with Parker Solar Probe as it gets even closer to what the densities are. But I mean, you know, collecting it, we could collect it in a bottle and return it to Earth, but it's going to still be a vacuum. I don't think, I mean, we'd have to get so low in the sun's atmosphere that I don't even think it would be possible with the technology that we have today. Because things, I honestly don't know. When you have collisionless gases or collisionless plasma, temperature is not what you think it is. And so you might be able to build something that could survive insane amount of temperature, but you'd still be collecting something that's so vacuous that it wouldn't be surprising what you see. I think what becomes more important when we talk about collecting samples from the sun is actually looking at what some of the heavier ions, what their freeze-in temperatures are. That tells us a lot more about what the dynamics of the physics that's going on there. So a sample return, I don't know if it's necessarily first feasible, even with the best technology that we have, and secondly, that it would tell us anything that we couldn't see remotely, at least from not necessarily from Earth, but from a much closer vantage point, like a mission like Parker Solar Probe or even Solar Orbiter. But I think those answers are definitely coming. We're obviously not going to get rocks out of the sun, so I'm not sure how valuable a sample return mission from the sun would be. But that's I'm sure. I'm sure scientists will be thinking about it, thinking how cool that could be, and what strange things we could do trying to understand it. But of course, having plasma analyzers and things like that right on board the spacecraft is kind of a sample. It's not really sample return so much, but it is definitely understanding a lot about what the solar wind is comprised of, both from the low species or the low mass species like protons and alphas, but also in the the heavier ion stuff. That gets to be much more interesting when you start talking about fission products. But then that goes into solar astronomy, which is a little bit out of my field because I'm space weather. So some of those conversations may be better with a solar astronomer than with someone like me, because I'm far more interested in the weather aspects than the astronomy aspects. But that's a good question. Okay, so let me get back to this. Here's a typical chronograph observation. This is old. I don't remember exactly which instrument this is, but I took this from Angelos Vorlitos' talk a long time ago. It was such a great little thing that he did. He wanted to show that you have a pylon, you have an occulter, you have here's the CME that comes out. Here's the front. Hopefully you can see that. Yeah, you can see that in the thing. Good. So that's the bright front. Here is the cavity. I don't know why the arrow is blue, but there you go. The cavity is right here. You can see where it gets kind of dim again. Know that in coronagraphs, bright stuff means density, high density. So there's something, you know, thick there, optically thick or thicker. And then in the cavity, it's very vacuous. So, you know, because it's dark. So you have a thick front, a vacuous internal part, and then you have the core. And that's this thicker part here. So we started to learn that there is a three-part structure, a front, a cavity, and a core. Now, that's the way they look in coronagraphs. But remember, this is all we had back then. Of course, we ignored things like streamers, right? That's what these are. These are from the solar wind. And, of course, the cosmic ray streaks. Here's a couple of them here and there. You know, you have random stars and that type of thing. Once again, these are things that a lot of people call aliens in coronagraph images. You know, space is hazardous, and there's a lot of stuff that happens up there. It's not the same as taking a picture with your cell phone. And I bet you if you took your cell phone in space and started taking pictures, you'd get a lot of really bizarre anomalies up in space with your cell phone that you wouldn't get down here at Earth. And that's because there's a lot of a lot of radiation, space radiation that's zipping all around all the time, that you just get shielded from because the atmosphere here takes out all that stuff. So that's what imagers have to deal with up there. So the neat thing is that with coronagraphs, you're able to get the mass, start estimating things like the mass of coronal mass ejections. And this is also for Angelos's talk, and this is why I took this. I don't want to go through the details of how they do it. But these are actually from his lecture. You could do something called the sector, where you just take the area, basically all in here, and you're able to do boundaries for CME lists. You can do it quickly. You can do height time measurements. It's all sorts of cool things you can do to be able to estimate the mass. You can also use just the torus of the front, and this would be best for flow calculations at a fixed distance. And then you can also use the center here, the core. And that is people do this most often to avoid things like streamers, adding mass from streamers and other planets and just other things because you're using a much smaller volume. So there's lots of ways that you can actually get the mass of coronal mass ejections or estimate them from just looking at the coronagraph images. They also can get flow speeds. I mentioned something about a height time profile. Here's an example of, you got a successive set of images here. And if you look at where the distance is, if you're looking in a particular direction, you can see how far from the center of the sun that is, how far it goes out. You're measuring the height. So in this case, it's this point. Here's the time moving forward. And here's if it's the center, you can go out in height. And as it goes up in altitude, you measure it going up in altitude and in time. And by doing that, then you're able to get an idea from the time, how long it takes, and from how high it's rising, how fast it's rising, you're able to figure out how fast the CME is going. So just from coronagraphs, we were able to get estimates of mass and estimates of speed, which becomes very, very important when we're doing space weather forecasting, for example, because you can do that from halo CMEs as well. So a lot of times that's why, if you ever see Nariaki and I, or even Chris Mosel talk about, oh, we just got a coronal mass ejection, or, big solar storm just launched from the sun, and then we say, okay, we're waiting for coronagraphs, or we're waiting for models. When we say that, it's because what we're doing is that we're waiting to see, as these images come in, how fast is this thing moving? Because that will dictate how long it's going to take before it hits Earth. So this is one thing to this day that we still find invaluable when it comes to coronagraphs, is that we are able to get simple things like mass and speed from just looking at these very simplistic images of a false eclipse. Another nice thing is we started to learn what the three-part structure is. I mentioned it before from Angelos's talk, but really it was this mission. This is the SMM mission, Solar Max mission, that really gave us that picture, a very clear picture. So you can tell the difference between OSO 7 and this one. Look how much more clearly you can see the evolution. Now we're starting to see the three-part structure. See here, here's the core, here's the cavity kind of vacuated in the middle, and here's the bright front. And you can really start seeing it here. Beautiful image of the front, beautiful image of the core and then this vacuous cavity. And then as it really erupts, things get a little crazy. But we actually have had papers written on this. This is Illing and Hundhausen back in 1986, where they defined from this image itself, as you can see, recognize? They actually drew it out, what the three-part structure was. And so this back in just in 1986, I was in high school in 1986. This is our entire picture of what coronal mass ejections were, at least observationally. And this gave us the idea that there are these three-part structure meant that there must be flux rope type things, that these are flux ropes somehow. These are those solar slinkies that are erupting from the sun somehow. But it wasn't really clear how that was actually happening. And then we started seeing, and as you can see here, tons of examples. Now, granted, these are from SOHO, which came later, but you can see these types they take all sorts of different shapes as they come out of the sun. There are just so many different types of angles, and we started realizing that these are projection effects. That you may have a solar slinky that's pointing out of the plane of the page here, but here it's kind of oblique. It's kind of sitting half in. And like I said, I wish I had my slinky with me, so that I can't really use that. So that it's actually a tube that's kind of looks like it's squashed, only because instead of being a perfect circle pointed this direction, it's kind of tilted and tilted up a little bit. And so now it looks more like an oval, an elongated oval. But we didn't really understand what we were looking at yet, because it was hard to go from this to this. And even when we launched stereo, I remember some people were saying, well, launching 2 spacecraft isn't going to make any difference. It's not going to help us understand any better than taking 2 cameras and taking a picture of the front of a cow and then taking a picture of the side of the cow and being able to put it together as a cow. And I always remembered that particular statement. I forget which one of my colleagues said it, but it was always, it might have even been the PI of the heliospheric imager at the time. I don't want to label someone as saying it who didn't, but I just remember back in 2002, I started laughing because it was such a visceral illustration of exactly this problem, is that we had all of these different angles of this structure that we could only partially see anyway. And if someone had never seen what a real cow looked like, and you took a picture of its belly, and you took a picture of its head with the horns, and said, here, put these 2 pictures together and make a cow, someone would go, and not know what to do with it. So that's kind of where we were with a lot of these coronagraph images, is that we were just like, how in the world do you get a coherent structure out of this? But it did all start with the idea of the 3-part structure, all from coronagraphs. Again, notice I have not shown you any on-disk images. And that's really critical, because it gets you to understand that, there was so much about coronal mass ejections that we were completely blind to in the beginning, even up into the mid to late 80s, in a sense. We were just completely blind to a lot of the on-disk stuff. And we had ideas of, and this is where flare ribbons come in, we have ideas of a flare structure that occurs on the sun, and with the magnetic models and our electromagnetic understanding of Maxwell's equations, we were able to kind of deduce that these structures somehow had been trapped and jailed by magnetic field lines that were coming up from these flare ribbons. And they somehow had managed to loop them and tether them down. And that these might actually be flux rope structures inside, but then you had this big plasma pile up in front with probably more magnetic field over it. And then, of course, as it erupted, these tethers were somehow cut or ripped or broken or reconnected, so that it freed all of this stuff to move outward. And so how you got the 3-part structure was that and some people were actually even able to see a little bit of a shock in front. I don't know if I will show an image that clearly shows the shock in front, but sometimes you can actually see the shock in front in a coronagraph image. And then you had this big thick front. That's what they're calling the plasma pile up here. The cavity is this section in here where there's nothing. And then you have the core, and that would be where the dense filament structure that we saw on the sun, where we'd see like an H alpha on the solar disk from ground observatories. We'd see like a thick filament that would be sitting right there on the sun, and then we'd see that filament kind of disappear, and out in the coronagraph would be this big, beautiful three-part structure, coronal mass ejection. So we figured, okay, this is the H-alpha filament that is being tethered. We've got all of this flare dynamics going on underneath, and off the whole thing comes once the flare ends up causing reconnection to happen, and the magnetic field is reconfigured, and it's let loose, and it's let free, and it all comes flying out. And we had, speaking of Jack Gosling, this is one of his early pictures about some of the magnetic loop topology. We're talking here exactly this area where here are the flare ribbons. This would be one side, one set of flare ribbons, the other would be right there. Again, I will go more into that when I start talking about flares in a different course. But as you have these loops here, that's what this loop is here. And what would happen is that these parts of the magnetic field would pinch in. And as they'd pinch in, because they were pointed in the opposite direction, they would reconnect. Remember, you never want magnetic field that's in opposite direction. That's when it reconnects. It would pinch off just like this. This would continue to lift off. You get soft X-rays, which would be the hot, really hot flare loops. You'll see me show them later as in a movie, post-eruption arcades, PEAs, you'll see it for short. But these are very, very hot. You'll see soft X-rays coming off of them. And sure enough, the whole structure, the flux rope would then erupt and fly off into space, and then we'd see it at Earth. And as time went on, models of what we now call CME genesis became a very hot topic. Here's just a couple things where people are talking about that. Once again, you can see the same kind of picture. Reconnection sites, flux rope, here's the CME. Here's the open flux where you can actually get communication from, let's say, an erupting area, communicating some of that and transferring through radiative transfer, some of that hot flux can actually go into the open flux, and you can see some of that escaping particles there. And then we started getting ideas that the magnetic field was actually looped around these structures, and this became the flux rope, trapping plasma and hot stuff in this core. And you could see how the evolution of the flux rope evolved. And then this was what was left over when this structure took off. You had these loops that were very, very hot and gave really beautiful, beautiful imagery. And I'll show you that in a minute. Again, I'm not trying to get into this too in depth because some of this I'm saving for the solar flare part. And if I tried to do all of this right now, it would just confuse everybody. It'd be just, this course would last forever. From the side view, if you were to look at this from the side, here again, here's that hot loop. These areas here. Here's where looking straight into the solar slinky. So this thing would extend out this way, but you're looking right down the tube of it. This part releases. Here's what they call the X line. This is where the reconnection happens between field that's going this way on this side, field that's going down on the other side, so like this. And so what happens is you get this thing releasing. This part lifts off. This part comes back down and stays with the sun. And when you started talking about what we wanted to observe, look at all these areas that people wanted to observe. You have the core, the sides of the acceleration, the hot flare loops, particle transport, the foot points on the sun, flare ribbons to look at. I mean, it was just, suddenly we had all these things that we wanted to look for to understand more about our idea of what the standard model, this became the standard model, what we actually thought was happening. So we suddenly had all these observational targets. But guess what? All these observational targets you're not going to see with the coronagraph, right? I mean, they're all on the sun. So pretty soon, we're going to have to start thinking about going from a picture like this to something where we're actually observing on disk. But meanwhile, as we were doing that, we were still using ground-based these are like chronometers, I think is what we called them. This was the Mark III instrument. And James Chen a good friend of mine, he took the whole idea of the flux rope structure from the standard model and began to really have it lift off. He had some ideas that were considered radical at the time, but a lot of them have been borne out to be true. And he's taken this structure and he started really pushing it out into the solar wind and really having it travel all the way to Earth as a structure like this. And it opened up a whole area of connecting solar structures to what would be the interplanetary counterparts. So be aware that happened right about this time. We started looking at this three-part structure and saying, okay, this answers one question, but it asks so many more. And we really need to get better imagery of what's actually happening on the sun and what's happening in interplanetary space to really be able to put this stuff together. Because we were seeing these structures as they pass over spacecraft at Earth and other planets, and it didn't really make sense to us what we were seeing. We were seeing flux ropes, and we were going, okay, yeah, it's got to be flux ropes. We understand that. But some of the orientations and just the way they looked seemed to be a little bit different than what we thought they would be. And so that was one reason why we knew that coronagraphs weren't enough. Here was another one. We have coronagraphs that, in this case, this is again LASCO, but we would have chronograph images that would do this, and they'd give us, let's say, a halo, right? And so we knew that at this point, that halo CMEs were ones that were coming toward Earth, or were they? Here's an example of a halo CME, and we saw on disk, this is later on, we have EIT with SOHO, we could see the solar source region. And here's another halo CME, but look, there's nothing on the front side of the disk. Matter of fact, you see a little poof here, but that's because the source is on the backside. But without these images here, can you tell the difference? Can you tell which one is front side and which one's backside? No. So we learned very rapidly that chronograph images of themselves do not provide the whole story, and that we absolutely have to rely on on-disk imagery of the corona to help determine the source regions. But we didn't know at the time that we were creating these images didn't exist. We didn't know really where should we start. Now we knew about the corona from eclipses, and we knew about our telescopes here on the ground. But the telescopes here on the ground would look at calcium lines or helium lines or something like that. We couldn't really image the corona directly, right? And why is that? Well, anybody who remembers my talk on telescopes, sunspots and telescopes, will remember this image. This is what our atmospheric window looks like. Here is our atmospheric opacity, 0 to 100%. Anytime you see it go down to 0 or close to 0, that means we can see through our atmosphere. Anywhere it goes up to the top here, up to 100%, that's where we can't see through. Okay, our atmosphere is completely opaque. And here is the wavelength range. And I've got down here another scaled reference of what these wavelengths mean. So here's the visible light window in just this area, and you can see it up here. There's the visible light window. Over here are gamma rays, X-rays, ultraviolet, extreme ultraviolet. Infrared is in here, microwaves in here, right? And you keep going down, television, shortwave radio, right? Standard band radio, blah, blah, blah. We have these windows. Here's the radio window that we can actually transmit. That's where a lot of our satellite frequencies are. So we can transmit from space to the ground, and we can hear the satellites and vice versa. And here is the visible and IR window, where we can look and we can see the sunlight actually hitting us in yellow in all the visible light range. And we can even see it clear down into heat. Here's the infrared window where we get the heat from the sun. That does penetrate our atmosphere. But if we go up into higher wavelength ranges, higher frequency ranges rather, like into the ultraviolet, into the extreme ultraviolet, and into the gamma rays, and into X-rays, that stuff doesn't reach us from the ground. So unfortunately, what that meant was that everything that was the corona, everything that the sun was emitting in the solar corona, was something we couldn't see from the ground. We just couldn't see through the atmosphere. So this became the ground-based part, at least part of the ground-based telescope problem. This is what the sun looked like with some of our best imagery as far as looking at coronal mass ejections from the ground. You'd have H-alpha images where you'd see filaments. These, as we understood them, became the core of that three-part structure, right? We'd see these things lift off. As a matter of fact, here's an example. Here is a polar crown filament, and look what's happening between these successive images. See it disappear? Partially disappeared, almost totally disappeared. We know an eruption happened, but what's it look like? Now, if we look at coronagraphs, we'll see that thing come out. Sure, so that really was our standard understanding of what coronal mass ejections were. The other problem about the ground telescope problem is that notice that these two images look alike, but this one doesn't. That's because these two were taken with Big Bear Solar Observatory, and this one was taken with the Moudon Observatory in Paris, in France. I believe it's France. And yeah. And this is the classic problem that we had back then. Ground-based observatories rotate with Earth. So if a eruption process takes many hours, well, your observatory that's watching it will rotate to the sun's or to the Earth's backside, to the night side, and we don't see the sun anymore. So now you got to get a different observatory to pick up the slack until your primary observatory comes back into view. And that's exactly what happened here. So now not only do you have something that doesn't have eyes on 24/7 of the sun, and then you got to calibrate images in between from different locations with different instruments, different optics, different everything. But also, you can't image the corona. So this is why space telescopes were absolutely necessary. So we thought, okay, well, we want to image the corona. Let's see if it can teach us anything more. But where do we start? Well, how about soft X-ray? We knew there were strong emissions in soft X-rays when there were flares. So that makes sense that that would be the first thing we'd try when we want to image, you know, the corona out in space. So we built YOCO, and we built multiple. We had a soft X-ray telescope, a hard X-ray telescope. The SXT, though, is probably the most famous of all of them. Here are some of the very first images of the solar corona. And why do we do X-rays? Again, because coronal emission is very strong in X-rays. We knew we would get good images. Here was the very first time. Well, these weren't the first images of YOCO, but these are you know, among YOCO's, among SXT's famous imagery. But this was the first time we ever saw coronal holes. We were like, what are those? Are those holes? You know, we had no idea what we were looking at. It was amazing. How could something be so incredibly well formed and not be emitting X-rays? How is that even possible? When you look at it from the ground, you don't see anything like that. How could it be so radically different? Now, YOCO was launched in 1991, and it revolutionized the way we looked at the sun. It also was the first space telescope to use CCD imaging. So now we had fast image cadences. We no longer had to develop film. We could take pictures and store them, and take pictures and store them, and do it at much higher cadences. So now we started to be able to see things like transients, like coronal mass ejections, much faster, in a much higher cadence, much faster than ever before. And you can see even here, here's something where you see a little bit of hot X-ray in this area, but as the thing rotates, look, you see a little bit more activity, and look, it changes, even more activity. And then something totally different as it rotates even further away. So we started seeing much more stuff like that. And it gave us much more insight into things like CME genesis. And as a matter of fact, do you remember this one I just showed you, right? Let's return to this polar filament example, but not from the ground. Now let's look at the same example from YOCO. I always love this example, it's amazing. So from YOCO, now granted, this is blooming, okay? This was a very active sun. These are active regions that are just very, very bright, and it's causing what we're calling these flares. This is not the sun blowing up. This is just saturation in the instrument. The reason why they went ahead and saturated the exposures, just like you can saturate the exposure on your regular camera and make everything go white out, is because they weren't interested in what was going on in the active regions. They were interested in what was going on down here. This was that polar crown filament. And for the very first time, they saw something new, really new. They saw hot loops, arching structures. They even saw connectivity as this thing, and they really made the exposure really bright for this one because they saw a connecting loop from what was going on with that erupting filament down there to something that was actually connected to active regions up at the equator. Something like sympathetic connections. So there is radiative transfer. There's energy being transferred even to areas that are far, oh, far away from where the actual eruption is occurring. And suddenly it just opened up this whole new world of, oh my God, the magnetic connectivity of these structures is far bigger, far more than we could have ever imagined. And it really began to give us insights into the mechanisms. And now just imagine, as we realized that in X-rays, we decided, well, what about other wavelengths? What about extreme ultraviolet? And this is when we decided to launch SOHO. We launched SOHO in 1995, and it came on with extreme ultraviolet imaging of the corona. And what we saw with SOHO just changed everything. Is that pretty cool? Here's the same SXT images of the polar crown eruption. And look what SOHO showed us. Now imagine how amazed scientists were when they could see CMEs like this, where they could see the source regions, they could see all of this stuff actually erupting in soft X-ray, but now they could actually see the material itself lifting off. No longer did they have to rely on coronagraphs at just a two-dimensional plane of the sky. They got a view of the disk, of the full disk, and this is what the sun looked like. It just changed everything. So this was SOHO back in 1995, and this is where we started really getting an explosion of things like models. And you think about, here, let me go back for a second. When you think about the three-part structure and what we had to work with, just a disappearing filament on the sun from ground observatories and a three-part structure in coronagraphs, and that was our standard model, to seeing stuff like this and this with its sympathetic connection. It's like night and day. So you see why I had kind of a little trouble putting this talk together without going into the history. It wouldn't kind of make sense. How did we get to that definition? Would you ever look at this and say, oh yeah, there's a three-part structure? No. And if we had started out, instead of thinking about eclipses and the corona that we could see during eclipses, which then gave us the idea of doing coronagraphs in space, right? I mean, how natural, how human. If we had somehow had some paradigm shift and had some dynamic, some divine inspiration that said, no, I think I'm going to look at the sun in extreme ultraviolet first, we would have seen this. Do you think we ever even would have had a three-part structure as a definition of a coronal mass ejection? I think it's debatable, to be honest. So to me, the history of how we discovered coronal mass ejections and what they were like was just as fascinating as the science in of itself. The process is really cool. So if you, again, we're in that Q&A I did with telescopes and sunspots and telescopes. This is also a slide from there. I just wanted to put it up to remind everybody. We have such an amazing range of imagery now, right? Here's EIT, here's some extreme ultraviolet, here's two different images from SOHO, EIT instrument, two different wavelengths. Here's YOCO, the soft X-ray telescope again. Here's the VLA instrument that's looking at 91 centimeters. And look how radically different the sun is. I mean, you can't even, in this one, you can't even see the perimeter of the sun. We had to draw it in because we only have a couple areas that light up at 91 centimeters. So look how radically different the sun looks. And then also we have SDO here with the day side of the sun. Here's stereo with its beacon images. You can just see, even having telemetry differences, how much it makes a difference to have fast, high-resolution images of the sun that help us determine really what the dynamics is. And it just lets you know, and it's just a good reminder of how incredibly observationally driven coronal mass ejection science is, and really so much of our field in heliospheric physics. It's very observationally driven, because if we can't see it, we sometimes, at least historically, we didn't even know it existed. So it's really neat to kind of go over and look at that. And when we go to the current day, we're so spoiled. We are so spoiled. SDO and now GOES, all the GOES R suites that have an instrument like AIA, the instrument's called SUVI, has a lot of the same wavelengths. Look at this. I mean, I call it imagery because we have the HMI, the magnetic field Dopplergram, and magnetograms on there that aren't imagery in the classic sense. But we have the white light imagery and 1700 angstroms, 45, 16, 304, 171, 193. Look at all these. I mean, I could just go on and on and on. We can look at so many layers of that onion, whereas so much of our history, we didn't have any of this, right? Yoko, our X-ray imager, which we don't have an X-ray imager of the sun anymore, not right now. So, well, we do if you consider SXI, but poor SXI has been, that's on GOES, it's been just beaten up. The CCD on SXI really was never designed for soft X-ray, and soft X-ray has really taken a toll. It's just too high of energy, and so it's really damaged that sensor, unfortunately. So if you do, I think it's GOES 13 that has SXI on it, that's an X-ray imager. But it's nothing like what Yoko is, and the poor thing is really limping along. Most of our imagery now is in EUV, as we've learned that EUV is good enough to give us the dynamics that we need to understand a lot of the processes. And we can go to really high wave or high frequencies, 94 angstroms and 131, to really look at flare dynamics. We don't necessarily have to go into soft X-ray and image the whole disk, which is a lot harder. But I'm sure we will launch another X-ray imager at some point. We just don't have one right yet. But remember, SDO with all of this was only launched in 2009. That's not that long ago. Think of all of the history had prior to that, where we're using a much smaller suite of instruments to be able to understand all of the science that is coronal mass ejections. So before I move on, let me stop here and see if I can find out if you guys have other questions. We do have more of the talk yet to go, but this is going to be a quick break and just see how are we doing here. Whoop, I got to slide this up. Questions. How about stereo B? Yeah. You get the same effect by simply changing the colors. No, you don't. Changing the colors, I hope you're not talking about just changing the colors here. You don't. You see radically different things. Remember the image that I showed? Here's an example. This is, you could tell, this is actually the same image because you have this same active region here. Look right here, look. Can you see that loop? Can you see that magnetic loop right there? In 171 angstroms, you get magnetic complexity. You could see rays sticking out this way that you would not see. You don't see that here. Look at this in 335. Look in 211 angstroms, where you basically just get the fuzz of the solar wind. You don't see that. And of course, 1600 Kelvin, you don't even see any of the corona. So even at 131 angstroms, you don't get those loops. You're only getting them at 171. So, you know, and if you looked at the image that I showed earlier as well, you could see a coronal mass ejection in 304 angstroms very well. But you didn't see really anything, maybe a tiny bit in 131, but you didn't see much in 193, that's for sure. And you didn't really see much in 211 either. So it really does matter what wavelength of the sun you're looking at, you know, to know what area, what part of that atmosphere you're trying to suss out. So that's, and that's the only reason why we color code them, is so that we, you know, it's just standardized. And unfortunately, it's not standardized in every spacecraft, right? Every spacecraft chooses their own color. In AIA, 94 angstroms is green. In stereo, 195 is green. While the closest we have for that is 193. It's 193 to 195 in an SDO. But in SDO, in the AIA instrument, it's brown. It's the bronze sun. So we don't use standard colors. So really, if someone says, well, the green sun, and you say, okay, great, what spacecraft are we talking about? What instrument? Because depending upon which instrument you're looking at, which spacecraft you're looking at, the colors may mean some other wavelength. So that's one bad thing. I mean, I wonder if we should have some cross-platform normalization. Okay, this will always be color-coded green. This will always be color-coded, whatever color. These visible colors are obviously not what you see in the image. And the image comes off as just exposure, bright and dark, probably shades of gray. We color code them ourselves to make them easy to identify without having to look at the actual wavelengths. But that's neither here nor there. Okay. Will it help if we put a camera on the top or the bottom side of the sun to measure the solar flare and other phenomena? Yes. Oh my gosh. Polar missions. Oh, don't get me started. Yes, we are fighting to get polar missions, mainly because of this. It's the magnetograms that really matter with the polar missions. We cannot get a good enough understanding of the sun's magnetic field to make the models that we want to make. Remember, the sun is electromagnetic. We need to understand the magnetic field configuration. We need to understand the electrodynamics and all of that, and it's all governed by by how well we understand the magnetic field, which is what we can measure, and at least measure reasonably easily. So without it, what happens is that we make models and we make assumptions, and we fill in holes with oversimplified an oversimplified understanding. And what that does is that it tweaks really where the equilibrium is of these fields. A lot of the stuff, the fields, the magnetic models we use are what we call potential field. What that means is that in a perfectly potential field, the magnetic field has a configuration and it's stable, meaning it doesn't move. What that also means then, if it's not moving and it's completely stable, then that means there are no electric currents moving around that field at that time. It's the lowest energy state of a magnetic field. And it's also the simplest. Best one to start with, right? We know that when you have flares, there's all sorts of electric fields that are generated when the field changes and reconfigures. Electric fields are everywhere. You can see it in the energy release. But when we just want to get a basic picture of what the Earth's magnetic field, the sun's magnetic field is doing, to then be able to figure out where the instabilities might be, we need to have that global view and have that underlying field be really well understood. Without a good image of the poles, we don't have it. And the reason why we fight so hard, why it's so difficult, is because it's so difficult to get what we call out of the ecliptic with these spacecraft. All of the planets move in the ecliptic plane, right? The same plane Earth is in. You ever notice all the planets are kind of in a row? We're all sitting kind of right around the equator of the sun in a nice disk. And we all rotate around the sun in the same direction in this plane. There are some things like comets and things that are tilted, sometimes at very high inclinations. But we've had very few missions, spacecraft missions, where we've done that. Ulysses is a classic example where we've actually gotten out of the ecliptic. The near mission is another, where we actually were visiting an asteroid, and the asteroid was out of the ecliptic plane. So we had to get a gravity assist to pop us out of the ecliptic plane. But these are very, very labor-intensive, thrust-intensive, expensive missions to get this kind of stuff done. So unfortunately, polar missions they're hard to convince the powers that be that we need to spend that much money, when it's so much easier to just fly, in the plane, in the ecliptic plane where all the other missions have been. So a lot of times those are the missions that get funded and not polar missions. But it's getting more and more critical, especially as stereo is showing, and hopefully as Parker Solar Probe is going to be showing, that we need these polar missions. And that's what we're really hoping for here soon. So hopefully that answers that question. Oh, okay, sorry. Bo has to go. Thanks, Bo, for being with us. And let's see, any other questions right now before I move on? Not yet? Okay. Let's see. Let me scoot down. And okay. Heliosphere porn. Okay. Yeah. I never really used that phrase before, but I might borrow it from now on. That's funny. Yeah, it can be if we get all excited about it. All right. And yes, I did finally take a drink of water. Let me also check Patreon real fast to see if anybody has asked me anything on Patreon. So if you guys happen to be Patreon members, I want to make sure that I am good to you. I don't see anything yet. 4 comments. No, these are all comments that I've already addressed. Good. Okay. That's wonderful. Okay. So now, moving on to how we look at coronal mass ejections now. There's so many different ways that we that we can look at coronal mass ejections, that we can detect them. We can detect them with now, this is back on the ground, looking at filament eruptions. This is a prominence from the edge on at Big Bear Solar Observatory. We can look at H-alpha images of filaments that are erupting. And we can look at filaments on disk, even in EIT or in extreme ultraviolet. But we can also, in extreme ultraviolet, we can look at dimmings around these structures, and I can show you some more of that. Here's some dimmings right here. We always know that is a very good sign of when coronal mass ejections erupt, and I'll show you some of those dimmings here in a few movies in just a minute. We also can see post-eruption arcades, the PEA. And they are arcades that, here's more of them right here, that these are the hot loops that we were talking about with the flares. And when I do the flare talk, the mini course, I will go into those in far more detail. But that's where you're seeing a lot of the hot X-ray stuff coming off of. And also from SXT, from Yoko, here is like what we call a sigmoid. And you can actually see these structures, the erupting structures. They oftentimes will take a shape like a sigmoid or a reverse sigmoid prior to erupting. And scientists will actually look at the direction of this and be able to tell which way the flux rope is twisting. They'll be able to measure things like helicity, handedness, all sorts of things. Then once that structure does actually launch from the sun, they actually will then see if we can measure it out in near 1AU or with a spacecraft, what we call in situ, and see whether or not they were correct. And sometimes they are, and sometimes they're not. We're still not completely there yet. Part of the problem is that we can't a priori tell what direction the magnetic field is pointing inside these structures very easily. We're getting better at it, but we're not quite there. Plus, when they erupt, they also have a tendency to rotate, and that is one of the biggest problems that we are dealing with, especially in these low activity cycles where we're getting a lot more of these coronal mass ejections that are erupting much more slowly. They seem to be much more affected by stuff in the solar wind and can get distorted a lot more than, let's say, a couple solar cycles ago when these structures would launch really fast, really hard, and they just plow right through everything. And their signature at Earth was far more consistent with the signature at the sun. It's what Janet Lumen and I have joked about many times is this isn't your grandmother's solar cycle, because there are so many things about these low activity cycles that we see that we haven't seen before. And a lot of the stuff that we knew and we took for granted, it's making us reevaluate as scientists. So it's very interesting from that point of view. Okay, so let's see. You want to see post-eruption arcades first? Let's do that. I'll show you some pretty post-eruption arcades. Come on, movie. And let me make it a little bit bigger. So here's something from Trace. And you could see something that's called the coronal rain. So here's the eruption, and you can actually see the rain coming down. Now watch these loops. So the CME already took off, but here's the post-eruption arcades. So the slinky is sitting this way, and it's kind of twisted around this way. But do you see how these loops, do you see them all? Here's some here, and then they loop over and back. I'll play it again. It's such a neat, this is one of my favorite movies from Trace because of this. You can see the eruption happens right there. These are all now the hot loops that are forming. You can see them forming here, all of that. And now you're getting all of this plasma that is raining back down to the sun. All this stuff is falling down. It's all coming down, and it's cooling. And I'll show you how we've actually simulated that. Anybody who's seen the recent NCAR flare simulation, I'll actually play that so we can see that in more detail. But here it is once again. The eruption has occurred. Now you're seeing what we call the post-eruptive arcades, and that's all those loops. And you can see them in real detail. It almost looks like an artist's rendition, but this is actual imagery from the sun, from an instrument called Trace that just did incredibly high-resolution observations of the corona. And can you see all those loops? That's all magnetic field stuff, and so you're looking at kind of the top of a slinky if it were kind of bent like this, and that's what you're seeing there. Hopefully we're back, okay. And so you see them here. You can see them pretty clearly here. The same kind of idea where before with Trace we were kind of looking at them edge on. Here you can see them coming from the top down. You can see those loops again forming this way. And you would have dimming regions on either side because the actual big slinky that took off would take off from this section here. And these dark dimming regions would be the regions that actually tore off from the sun and created, believe it or not, little mini coronal holes. Transient coronal holes, we call them. But you can see before, here's kind of the filament, kind of remember the sigmoid kind of S-shaped structure, and that whole thing lifts off, and afterwards you've got these really dense loops, you've got the dimming regions, and there you go. And I'll play this movie so you can see a couple of them in different wavelengths. Now I'm going to fast forward through some of this because this is a much larger film. What I really want to get to is about what happens here in just a sec here. Okay, so we're looking at sunspots. Here's the chromospheric layer that's 304 angstroms. And then you'll see a beautiful 304 angstrom image of a prominence eruption. Do you see that erupting like that? Do you see the kind of the tornado twisting? That's all the magnetic field jailing. And you could see that really as a big flux rope structure because it twists. Here's coming out into the corona. Remember, these are the coronagraphs. This is our first view of what CMEs really were. But here's what I wanted to show you. We're going to show a flare. This is going to be a flare that's going to be associated with a coronal mass ejection. And watch in just a second. You see here's the loops coming. Look at the waves. Can you see the waves go by? They'll show it up close again. Right here, watch. Boom. Do you see that? Do you see the dimming regions and the waves going by? Here's those were the, let me go back. Let me go back just a little bit. I should probably pause it. Right through here you can see. Do you see that wave shoot off? Back and forthing it right now. See how it gets all dim in that region right in there? That is a dimming region. A wave gets shot off, and I'll show you. I'll talk about those more in a minute. And then these are the bright erupting loops. These are the post-eruption arcades, the PEAs. You can't see them. It's saturating the image so much, but they're actually loops that are completely lit up because the plasma is so incredibly hot, and they're giving off X-rays and everything else right now. And it's just, it's just stunning. And again, in 304 angstroms, here's that, oops, oh shoot, hold on. Sorry guys, I meant to hit pause, here we go. This is that famous picture, I'll pause it right there. The famous eruption, everybody's seen this thing to the point where they're probably sick of it. But here's the material. Oftentimes in this case it was a filament, so it's just a ton of material that was coming off. Back in the coronagraph days, this would be seen as the core. Right? You'd have a cavity in front of it and then even a bigger pile up in front. So this would have been the core of the material coming out from a coronagraph view. And you'll see it, as a matter of fact, I think it shows it right here when it shows a coronagraph. Hold on a second. There it is, boom, this stuff. So this was a three-part structure. It's kind of blown out now, but here's the front, here's the cavity, and here's the core, part of the core. Well, a prominence leg here and a prominence leg. But look how much you're missing. You just saw that big thing off the center disk. This is all we had when we had coronagraphs. It was just an image like this. Can you get a really good sense for how much more we've learned about these structures because we have on-disk imagery along with coronagraphs? It just blows my mind sometimes when I think about it. And then on top of that, we have things like EIT and coronal waves. Here's a difference image. You're actually seeing an eruption that just spreads out. You can see the bright front and then all the dimming stuff. This is, like I said, a difference image, so it's really just amplifying the wave part. But these waves are often referred to as the CME ground track. By following these and seeing how extensive they are, we can really tell how much of the sun was involved. And it really, because a lot of times, and I don't know this for certain, but I've always looked at it kind of like if the wave actually reaches a certain area on the sun, there's a good chance that there's going to be some type of reconnection going on. There's going to be some kind of cutting and release of energy so that part of that area, the magnetic field and stuff in the corona in that area will have been ripped off the sun and become part of the solar wind blowing out towards us. So the bigger the EIT wave is, oftentimes the stronger the coronal mass ejection and larger the coronal mass ejection is. So we've been able to get a lot of good information about that. We've been able to get things like expansion rates of the coronal mass ejection and seeing the connectivity to other sympathetic regions. Here's a classic example is Halo CME. This is from September of 2017. He did a dimming region. This was from that monster flare that launched a Carrington, what we think is a Carrington class CME. And this is the EIT wave, if I can actually, if it'll let me go to it. Come on. So here's his tweet, if it loads. And come on, play for me. So if you haven't seen this, he's got this pinned on his profile. Look at this. So there's the flare. Look at this EIT wave. Whoa! This thing, watch it. It goes around both poles. You can see it interacting clear up to here on the backside. Watch the, around the south pole, it goes clear up to here. I'll show it again. All the way around. And then in the north, watch it. All the way around to here. Again, all the way around to here. This thing was massive. And this is the EIT wave. We were only able to see half of it because the flare, believe it or not, when it occurred, didn't even occur on the Earth side of the sun. It occurred on the back side, just a little bit. We were able to catch the edge, the fringe of this flare, but the flare actually was what we call occulted. It was actually on the back side and partially shielded from us by the sun itself. And this flare was still massively big. I think it was the second largest flare of this solar cycle. It was like an 8.2. But this thing launched a coronal mass ejection that was so large, it's like having a gun pointed this way and firing it and having the bullet hit you. That's how big this thing was. Insane. And we knew that as soon as this flare went off because of the extent of this EIT wave. We went, oh my God, this thing is huge. We knew that it had given an eruption, and this EIT wave was how we knew how intense it was, engulfing both poles. And at the time, let's see, what did Nariaki say about this? 8.2 flare from this region was impressive. Coronal wave went past both poles. Big proton event, meaning radiation storm, likely a ground level event. EIS must have seen the plasmoid ejection. So this was an insane event. This is being studied still to this day. The radio blackout from this particular flare was so bad. This was when Irma was bearing down on Puerto Rico, and amateur radio operators, all the emergency responders, were having a nightmare of a time because this blacked them out for something like 4 to 6 hours. It was just an insane, insane event from all angles. But from the CME point of view, this is what was so cool about that EIT wave, is that we knew as soon as we saw that flare that this EIT wave showed us that the extent of this structure was massive. And yes, just because it was fired on the backside, because this EIT wave went as far as past central meridian, that we could get hit by it. And guess what? We were. We were hit by the edge of this coronal mass ejection. It was so big. Anyway, oh, I love that event. Okay, so speaking of, there's some of the flares we've been having recently. I've been kind of trying to pay attention to it. Don't know if I'm doing a great job. So with all of this going on, and all of these new observations and understanding of CMEs from all these different areas, there is no shortage of CME genesis models now. Here's one of the first ones, the CSHKP model, because it was made by Carmichael in 1964, and Sturrock in 1966, Hirayama in 1974, and Kopp Neumann in 1976. So they just took the first initial of all of these people who came up with it all at once and called it the CSHKP. And as you can see, it's very familiar, right? You've got the magnetic loops, you've got the flare, the hot post-eruption arcades sitting here. There's the flare ribbons we'll talk about later. You can see the arrows coming in to pinch, close, and allow this plasmoid, which is the core of the three-part structure, to lift off the sun. And there we go. After that, we got a little bit fancier. We saw magnetic structure of filaments from Lowe and Hundhausen in 1995. We had DeVore and Antikos back in 2000. This started to become the breakout model. And then we had Balugian and Martins back in 1989, beginning to talk about shearing and how you could actually make a flux rope from these, from just sheared arcades when they'd reconnect. You see that little post-eruptive arcade loop right there. So it took two sheared lines, you connect them together, one of them, you get a post-eruption arcade, and now you've got a field line that's actually looping around another one. After that, we started getting even more into it. We started getting into numerical simulations a little bit. Here's the flux cancellation model from Linker et al. You have a tether cutting model where you're actually cutting, having things being tethered down in certain places, and if you were able to cut certain parts in certain regions, you were able to then release and have the thing rise, get to a point where it becomes unstable, and then it goes. We still see that to this day when we're looking at filament structures. We see little activations, and that we pay attention to whether we see a little X-ray glow in and around, any bright points in and around a filament, because that shows like the filament's been activated. Sometimes you hear Halo CME talk about that along with myself, and we just keep paying attention to see if little bits and pieces of reconnection are happening that cause the filament to rise and rise and rise, because if it gets to a certain height, it could actually go unstable and erupt. We also have, let's see, more flux cancellation models and a loss of equilibrium model from Forbes and Eisenberg back in 1991. Pay attention to this because this will become very interesting a little bit later on, but keep your eye on this, especially this kind of idea where you've got this, what looks like almost a single line of connectivity holding onto a big bubble. That becomes very important later. And realize that this was done back in 1991 from Forbes and Eisenberg, just shortly after we launched Yoko, and before we even launched SOHO. So we had ideas of this stuff. Here's the breakout models. You see things are getting a bit more complex as time goes on. This is Antikos's, where is it? That's McNeese here. And I know this is the breakout model. Yeah, I recognize it. And I'm trying to see if where shoot. Okay, it must have been from his paper. Oh, Lynch. Oh, it's Ben's. Okay, so Ben Lynch's paper. This is recent. I was looking for any type of citation. So this is Ben Lynch working with Spiro, breakout model. It's very well known. And as we get even further into the numerical age, now we're getting really good simulations. As you can see, this is Taruk et al. From Predictive Science. Anybody remember Predictive Science? This is the company and the set of folks that did for the the solar eclipse. They did that really cool prediction of what the solar corona was going to look like, and they really were very spot on, except for one small place because we just had an eruption in that area. There was a CME that got launched, and it kind of changed the configuration a little bit. An area that had been closed was now open. So it only changed the corona by a tiny, tiny bit. Outside of that, the predictive science model of the of what the solar corona was going to look like was very spot on. This is the same group of folks. They're very good colleagues. I love these guys. And as you're seeing here, here's 3 flux ropes. What they're talking about is kind of a sympathetic eruption. You have one of them that begins to go unstable, or wait, which one goes first? Okay. Let's see, A, B, C, D. Okay, so this one it begins to rise and emerge, but this one here, you get a reconnection line here on this one. That allows this one to break out and kind of break its tether, its little hold. It becomes even more unstable and rises as this one now completely releases. But by doing that, then it causes another reconnection formed here. And then this second one will go off. So you can see how by having this thing get loose, how it affects something nearby, and you get this sympathetic set of eruptions that may not have happened if these things weren't so close together. You can actually get something in one area that destabilizes something nearby and causes it to go, where otherwise it would have stayed in a more stable configuration. So we're seeing these types of things in the numerical models now. They're getting far more they're getting far more advanced. And here's just an example of one of the many types of models we see. If you want to see how some of these numerical models work, here's just a very simple example of a flux rope forming. You can see we have tons of magnetic field lines in through here. And there's the foot points, there's the magnetic foot points, and you can see different polarities of the flux emergence and different polarities of the magnetic field, and you can get these structures that then erupt. And that's pretty much the way these models have gone for quite some time. And there is no shortage of types of models, and I'm not even beginning to advocate one over the other. Here's an example of how much is being done. Here's the mechanism, here's the reference for it. In triggers, we have sunspot rotation, twisting of overlying field. All of these are models. Shearing of arcades, reverse shear, self-induced shear flows, magnetic breakout, tether cutting, converging flows and flux cancellation, flux decreases. Look at all the papers. I mean, there's not just one person working on these things. There's tons and tons of people. More mechanisms. Flux emergence, close below the flux rope. This is flux emergence into a potential arcade, into a sheared arcade. Helical kink instability, flux transfer feeding, tilt instability, double arc instability, different drivers. You could have torus instabilities or flux rope catastrophe or a loss of equilibrium. I mean, it's just crazy how many different mechanisms now we have that we think are part of the process. Are some of these wrong? Yeah, probably. I mean, our models are still simple enough that they can't even begin to get all of the, they can't even begin to capture all of the dynamics. They can't even begin to suss out all of the quantitative variables of things that we need to take into account. A lot of this stuff is still, it's quantitative in its own right, but it's scaled down. It has to be, because we couldn't get any of these to converge otherwise. And there are so many simplifying assumptions that have to be made in order to make these things work, because we don't have direct measurements on the sun. We only have remote sensing. And so we can't know. We can only guess at what really is happening over there in the corona or at the surface of the sun. And a lot of it we can't even see into yet. There's all sorts of areas of solar physics that really aren't developed as much as they need to be, and we're still trying. Like helioseismology, for example, is a classic one. It's something that has the potential to be so incredibly powerful, but it's just not there yet. And if you want to learn more, there's tons of review articles that you can look up. I can forward this if you can't read it, and I can't tell if you can read it or not. It doesn't look like you can. But I can put this up on Patreon or you know, give you a link to it, to the paper that goes through this review process that shows all of the different types of things that we are currently looking at. And even with all of that, we're still coming up with new ideas and new ways of doing modeling, because now we have multiple spacecraft, right? So you have SOHO, you have stereo ahead and behind. Here's an example from Angelos from Vorlitis, I guess in 2018. I didn't realize he just recently published this. I thought it was a little bit longer than that. And it's multi-spacecraft modeling of the geometry of a CME. So take a look at this movie really fast. And so you've got a CME front, and you've got the center of the CME. And look at this. You're able to use the observation, even in a coronagraph, to constrain, because you've got the 3 different views, you're able to constrain what the shape of and the geometry of the structure is as it moves out of the solar disk into the heliosphere. Look how far they've been able to kind of show that structure as it moves out. So now we're just beginning to do this type of thing because we don't have that many observations from multiple spacecraft locations. And models are just beginning to get robust enough, and our coding ability as well as our computational ability, we're just beginning to get to a point where we can really start doing this stuff and use multiple vantage points for constraints, for model constraints. So that gives you an idea of where we are to some degree. And then the next one. This is what I'm calling the next generation of numerical simulations for CME generation or CME genesis. This is where we are now. This is where we're going. This is a paper that was published by a wonderful group, some at Lockheed Martin, some at NCAR. Scott McIntosh is on this. I'm very happy for him. And it is a magnetohydrodynamic numerical simulation with radiative transfer in here that just 5 years ago was probably computationally impossible. I mean, the fact that we're able to start adding some of the details that we before have always had to ignore or oversimplify simply because we couldn't, the codes just, we couldn't get it to process on a system, even on supercomputers. It just was too computationally intensive. And so and I won't go into the numerical issues. I was almost thinking of starting to talk about numerical grids and numerical diffusion, and I mean, there's a whole host of stuff that becomes very painful to talk about, where because you have to follow each parcel of plasma and know the magnetic field at each point, the tighter you make those points, the more computationally expensive it is, but the more you can account for things like numerical diffusion, which are, to some degree, it's kind of an error, a built-in error, because you have to kind of bend things when you do it numerically. It means that there are going to be types of errors that are unphysical. They're not part of the physical, the actual physics of the process. They're part of what happens when you build a code and try to run it in a computer. You end up creating errors that wouldn't be there otherwise. And that's something that people have, you know, there are all these sorts of adaptive grids and all sorts of ways that people try to get around it. And a lot of them I don't even know, because I am not a numerical coder. I just know that any time people talk about it, it seems like such an incredible headache that I'm so grateful I'm not a numerical coder. I'm very happy to be an observational heliophysics physicist, because this stuff would probably, I'd pull my hair out. But my hat's off to these guys, and what I'm about to show you is, and we're close to the end, by the way, but what I want to show you is this this movie that they created of this simulation that they did of, and they're calling that simulation of a solar flare, but you'll see the eruption. The reason why I wanted to show it to you is because of the actual coronal mass ejection that is in it. And here's the team. As you can see here, Scott McIntosh, he got a little, you know, hand wave here at the end. But these guys are an amazing set of colleagues. And again, if you want to see the paper, it's in Nature Astronomy. And it just came out recently. But this is where our modeling is going, and I'm extremely excited. So I'll let this play. And there's a narrator. When you actually watch the movie, there's a narrator. I'm not going to let the narrator talk. You can actually see the words up on the screen, just because I don't want to, it may not sound right because it's going to come through my mic, and so it's strange. But you're seeing here, there's the eruption. Okay, hang on, I talked over this. I probably shouldn't have done that. Let's try again. Okay, so as this thing plays, oh, come on, play. There we go. Oh, come on. Don't do that to me. Let's try again. I'm going to start it from the beginning. Hopefully this time it'll be better behaved. Okay, here we go. So it's starting with this eruptive region here. It's going to become very hot. There goes the CME being lifted off, and now you see all this green. All this green are hot loops. These are post-eruptive arcades, and there's coronal rain that comes down from them, and that's when they cool down. And so when the narrator goes on and starts talking about this, I think you see on this side, once he goes through this this very basic description of what's happening, they'll start talking about how this transport model, how it's color-coded. And really what they're talking about is, what they're showing is the temperature of the loops that you're seeing. You're not actually seeing magnetic field lines necessarily. So violet is the very dark, and the violet and blue are the cold, and then you've got red that's kind of an intermediate, and then of course white and green are going to be the very, very hot stuff. So here is the coronal mass ejection that's just about to be launched out. That's going to be, you're looking at the solar slinky from this point of view, and it's going to be kind of launched out this way. And then, actually you're looking at it from this direction. And then as it goes up here, see how it heats all this stuff? Look, you even see red here, and I mean green and yellow here. This is the sympathetic connection I was talking about. How you can actually get radiative transfer into loops that don't even connect with the actual region that you were looking at. This is what we first saw, and I'm going to pause this. This is what we first saw with Yoko, right? When we first got Yoko up there and looked at the SXT, and what they saw in one of the exposures, when they really overexposed it, they saw that polar crown filament. And when they did that, they overexposed, and they saw that one connection that went up to the equator and connected to another bright region, you know, at a totally different latitude. They went from the pole all the way up to the equator. Same kind of idea here, that you could actually have an eruption that occurs at one, in this case, active region. The CME launches, but then the reconfiguration and the radiative transfer of heat and energy could actually go and help reconfigure all of this, including up to another coronal field line or coronal, loop. And you transfer all of that energy into yet something else that can make that go unstable. So the fact that we're not only getting numerical codes that are good enough to actually cause an eruption, and then you can see again the post-eruption loops, the arcades, the PEAs, and as they cool, you see all this green turn red, and what they're showing basically is that all the hot stuff is draining back down to the surface, because as it cools it gets denser and it pulls back down to the sun's surface. So this is all the coronal rain that we see in the actual, like in that trace video I showed you. So what's cool here is that we finally have a numerical model that's just getting good enough to be able to show not only the eruption, but also show the post-eruption arcades, show the radiative heat, how the plasma is behaving, as well as how the magnetic field is behaving, and even sympathetic connection to other regions on the sun. So we're really beginning to enter a whole new era in which we're looking at the sun as a system. And that is so important, because this is where we get away from just our myopic views of transient eruptions on the sun as being a one-off, as being a single event that is isolated from everything else. And we start getting into what is far more like weather, just like weather at Earth, right? One thing leads into something else, which leads into something else. You've got things that are interacting with other things. And if this doesn't stress how much we need to know what the polar field of the sun is doing, for example, I don't know what does. Because if we're beginning to realize that even in an eruption, a coronal mass ejection eruption, or in a solar flare, that there's radiative, that there's transfer of heat and energy into sympathetic regions, then we have to know what these regions are doing, what they look like. And if we don't know what they look like, if we can't characterize them, we can't just characterize the local field anymore, the local topology of an active region anymore, and expect that that's the whole story. We have to know what's going on in disparate regions, distant regions of the sun. We need to know the global field of the sun, and we need to know it far better than we do. And we also need to know the plasma configuration of the sun, not just the magnetic field, but the plasma as well. And I think that's what Parker Solar Probe is really going to help us do. So this is why this is so groundbreaking. This is why this particular model is really what I would be considering the next generation and really where we're going. So here he's talking about, oh right, here he's talking about the polar rain, the coronal rain. See how hot it got, how cold it got? It went red. That meant all that hot stuff drained out. Yeah, and this is called coronal rain. Right, I forgot he put that in there. Oh, let's see it again. Shall we see it again? I'll let it play this time, and now I won't. I'll just let you guys watch. But these are the sunspots right there. There goes the eruption. There's a coronal arcades, a post-eruptive arcades, and then it cools down. And this area cools down as well. So that's where we think the next generation models are going. And it's just great to finally get computations, even on this scale, that we can see, where we can see how much more like a system that we need to, that we need to view this, that we need to view the sun as. Okay. So that's where we're going. Where have we been? And I've only got two more slides to show. So this is one, and one more after this. The one after this is more fun. This is part of the 1972 Carrington class event that Dolores Knipp just recently published. And we've got a lot of noise about this. I mean, it is just making the rounds on social media as well as in a lot of the scientific arenas. It's wonderful to know that we have such a stellar event to show serious Earth effects during the space age. But if you remember, 1972, what did we have up in the sky? At the time, we had coronagraphs. That's it. We had OSO 7. That's all we had. We didn't have anything else. I mean, this was in the early days of even seeing a coronal mass ejection. So prior to this, we really didn't know anything. We knew filaments disappeared, right, because we could see them from the ground. But we really didn't even know if we could see the storm, the coronal mass ejection lifting off of the sun at all. So that's what we were working with. And as a matter of fact, these are some of the few, well, there are a lot of images, but these are the nature of the images that we had back then. We had full disk images from Paris. You can actually see the flare ribbons from one of the flares. Here's the sunspot that you could see. I think this might have been a magnetometer image. This is a calcium-2. So you've got, you can see the filaments here. And then this looks, I don't remember if this is also calcium or not. I don't know, this isn't, because you would be seeing this stuff. I forget what this is. If this is a it might just have been white light, I'm not sure. I'll have to go back and take a look. This is from the Big Bear Solar Observatory, and you can see a filament here. You can see all of the different sunspots in here. Boy, this thing was a nasty bugger. There was so much shear, and even the images that they had back then, which weren't very good, just showed this thing as just an incredibly ugly structure. And it gave us this particular region, the McMath region of 11,976, gave us 4 solar flares that were monstrous. It gave us a ton of others, but it gave us 4 X-class flares. It gave us a couple very rare white light flares, which we don't normally see. In other words, you could see them with your eyes. And that's with the Carrington class event. That's oftentimes what happens. And you had 2 on August 2nd. We had 1 on August 4th. This was called the Grand Flare. And then we had 1 on August 7th. This was called the Seahorse Flare. And I actually have a video of the Seahorse Flare, which I'll show you in a second. But we had the Grand Flare was an X20. And it also gave out gamma rays. It's one of the first, I think the first in the space age to give out gamma rays. But if you recall, you notice, well, first of all, you notice there's no OSO 7 imagery of the CME, right? Anybody know why that is? I'll just tell you, these flares were so intense and they let off so much solar radiation. Do you remember, and particle radiation, do you remember when I showed the LASCO imagery where you saw the blizzard, right? When you get really big flares and you get particle radiation storms, you get a blizzard of particles. And I imagine OSO 7 was obliterated in terms of its instruments. I know there were a lot of, the gamma rays that it saw were off scale. I do know that I read incidences of OSO 7 and it said that its instrumentation was pegged off scale. So its imagery wouldn't have worked at all. They had just had no idea what they were getting into when it comes to going into space and trying to measure these things. So the fact that we had a Carrington class CME while we had OSO 7 up there trying to capture them, it just, it just happened to be good or bad luck, I'm not sure. But it gave us a real wake-up call and let us know that we really need to get on trying to figure out what these structures were. There was a disappearing filament. There were several of them. We had a CME that hit Earth on August 4th. I think it's the only record where we actually had the CME moving so fast that it actually hit Earth the same, what we consider the same day, within 24 hours of it hitting, of the flare occurring. This thing was going something like 3,000 kilometers a second. Fastest I think we've ever seen. The radiation storm disrupted many spacecraft and their instruments, and there's a whole litany of that, which I can talk about next time. I'll talk about this far more when I talk about the solar wind side of coronal mass ejections, because we can go over all of the stuff that has to do with the impacts at Earth and what we see. That's a much better course for talking about Earth impacts, because the solar wind is so much a part of that and the travel from the sun to the Earth. It destabilized portions of the North American power grid. It rattled the Earth shield so much that the changing field triggered sea mines in Southeast Asia to detonate. Basically, the sea mines thought that a boat was going by, a metal hull was going by, because the magnetic field, the local magnetic field, would change if the metal hull, if something metal was nearby that mine. And in this case, it was just simply the Earth's geomagnetic field changing that triggered the sea mine. And so it detonated a whole bunch of them. Long duration radio disruption with signals up to 1 gigahertz or past 1 gigahertz. That, when you think of radio disruption at 1 gigahertz, well, there goes your satellite phones. There goes Sirius XM radio. There goes GPS, GNSS. 1 gigahertz will wipe out that. It'll wipe out a lot of other telecommunications. Not to mention, of course, all of the havoc that would be wreaked around the, with all the particle radiation and everything else going on. This would have been, in today's day and age, it would have been insane. And the idea that we never even really saw it coming, because this is all the observations we could do, it's pretty insane. So let me show you one of the flares. This is all we had back then. Just keep in mind that this is all we had. This is the seahorse flare. This is the one on August 7th. This is the best we could do. That's it. Did you see any coronal mass ejection? Do you think we could see much with that? No. Without being able to image the corona, there's a lot we can't see. But there is a responsibility we have, and this is my last slide. So that was then, this is now, but meanwhile, in a galaxy far, far away, we have aliens at the sun, fueling, right? Let me show you a movie. And I'll just sit here and let it play, and you guys can watch this. Has anyone ever seen this movie? I love this movie. Anytime I want to get a good, anytime I want a good sanity check, I check out movies like this. So this is one of many that you find on YouTube. And, there's a circle. What could that be? An alien sphere launching. Oh, yeah, I guess it fueled, huh? Look at it. Let's look at it more closely, shall we? Come on. Show it. Yes. Okay, there's Earth to scale. Here, look at this. It's sucking up plasma blob. Look, there's one, not one, there's two of them. Why would there be two spheres? Remember the standard model of the CME? Remember they had multiple loops being connected? Slow motion. Okay, let's see. In slow motion, what do we got? Yes, wonderful. We've got a tether. Okay, interesting. And look, pretty soon, look at this. What's this? Maybe that's an overlying, I think at one point we see an overlying break of an overlying tether, kind of like maybe the bright front of the three-part structure, maybe. Come on, where is it? He slowed it down so much because you really got to get a good look at this. This is really an alien craft feeding off of the sun. I think this video goes on for something like 4 minutes. It's insane how much this person tries to pick apart every little aspect of it. And I will eventually lose my patience for it if it takes too long. But I just thought this thing was so funny. Come on, are you moving or what are you doing to me here? Yeah, it's moving. Very slow motion. I guess he really, oh no, now we're going to zoom in. You didn't see it closely enough. Yes, okay, right. There is a sphere and there is material all around it. And at one point this material kind of lifts off, right? Maybe that's the overlying tethers being, kind of coming off of the sun, maybe a little pre-reconnection, maybe loosening it, allowing the structure to move up a little bit higher in the atmosphere. And what do you think that might do? Maybe destabilize it a bit more, right? Because maybe this isn't what he thinks it is. Maybe this is magnetic field in here in a cool area and all this hot plasma is what's being illuminated in this wavelength. Maybe if he looked at this in 304 angstroms, he'd see a totally different picture with maybe a lot of hot plasma up here, right? Instead, he sees a cool plasma in this area, in this wavelength, and he's seeing what look like spheres. All right. So what is he really looking at? Well, lucky for us, we've got some very talented scientists. And matter of fact, one of the most famous of us, one of the most revered of us, is Nat Gopalswamy, and I love him. He's one of the fathers of CME physics, and he actually did a study on exactly this event. And so here's the cavity. Didn't we talk about a three-part structure? Cavity, core, and a bright front, right? The bright front already broke off. Here's the cavity. Here's the prominence. Oh, look, that's the leg of the prominence. It's a P leg. Once it erupts, you have A, B, and C at 3 different times. Here's the P leg of that, the prominence leg of that structure as it rips off. And look, we're actually, like scientists, looking at it not just in slow motion and in zoom, but we're actually looking at it from other wavelengths on the sun. Oh, and we're also going to use a coronagraph. Funny how scientists have a tendency to look at things from more than one vantage point to be able to assure they're actually seeing the whole picture. That's kind of the difference between alien nuts and, people who are actually do this kind of thing for their job. So here's EIT. Looks like this may be that's SDO. We may be looking at this from stereo. I don't know. I'm having to see which. No, this is LASCO. This must be EIT from SOHO. Okay, so this is SOHO's EIT. Slightly different wavelength than this. This one I think is, I forget where SOHO EIT for green. Is that 94? I can't remember. I think it's 94. So slightly different. We're looking at the source region on the sun. Then in coronagraphs, we're beginning to see that corona, the CME bright front come out. And here's the core in here. That's the prominence material. You can see the cavity. You can see the bright front. So what was an alien saucer sucking up energy from the Earth, or from the sun, in a coronagraph actually is a beautiful 3-part structure that we've known for many years. And remember I told you to pay attention to this picture? This is 1991, I believe, was when this model was created. Do you see this? If this is the cavity area and this is the tether, doesn't it look eerily similar to what this structure looks like? And as this begins to move out, This gets longer and eventually breaks, and then you get the CME launch. So, you know, these aren't aliens. These are coronal mass ejections, and we see them all over. We see them everywhere, and we even do, you know, height time drawings. Remember I told you about the height time curves to understand, and in this case he's not only just understanding where the leading edge is going, but where the prominence edge is going, where the CME core is going. He's tracking all of the different aspects of this structure because they all kind of move at different rates. And because that tells us something about the initiation of these things. And we're even looking at them from other points of view to be able to, from in this case, stereo B, to be able to understand what really the structure is doing and what the real dynamics are. But that's the thing when it comes to looking at coronal mass ejections. You have to look at them from all over. You can't just look at them from one wavelength and think that you have the whole idea. And we learned that through trial and error with coronagraphs. Because once we got past coronagraphs and started looking at the CMEs on disk, our whole picture changed. I mean, it didn't change. It changed, but it grew. It got so much bigger to the point where you see where we are today with that NCAR video, right, with that simulation. So this is really where I'm going to stop. This is it for the coronal mass ejections and aliens mini course, and I am ready to answer questions if you guys have some underlying questions. Remember that this story does continue. It continues into the solar wind as these structures are now convected out with the solar wind, or if they're plowing through the solar wind and driving shocks and all sorts of other phenomenon that go along with it on their way to Earth, where they hit the Earth's magnetic shield and they create a ruckus. In some cases, like in the 1972 Carrington class event, they detonate sea mines, and you have to wait 30 years for the military report to be declassified. Or, you know, they could be as gentle as, you know, some of the storms that we saw just not even a year ago, where we have these stealth CMEs that are coming out and that are so wispy that they need a push from behind with some fast wind in order to make them effective enough to give us a decent sized storm. So there's a whole zoo of these structures, and as I go into the solar wind, I can talk more about those and give you a better idea as to how we study them and how much the solar wind side of things have really added to our understanding of these structures even on the sun. So, all right, so let me go ahead and take a look, see what you guys have been asking, if you've been asking questions thus far. Let's see, astrobiology, This is a long shot, but could think that plasma have own gravity and magnetic field in that moment. Remember, everything is, when it comes to the sun, you're always fighting the sun's gravity. It's always a fight to become part of the solar wind expansion. So, you know, I mean, that's the whole reason why the sun manages to remain a sun, is because you've got this huge constant thermonuclear explosion going on, but it's the force of the sun's gravity that's pulling it all back constantly. So it's just like the gravity here on Earth. It's just a hell of a lot more massive, you know, stronger. And because of that, we can look at things like buoyancy. We can look at things like density. And we can look at that and how that changes, you know, how when things cool down, they become more dense, they condense, and they actually will fall back to the sun. If anybody wants me to, I'll play I think I have another video here of a beautiful example of coronal rain that just happened for like hours and hours and hours, and you can actually see it coming down off of the post-eruptive arcades and just raining down. It really looks like a rain, but it looks like a rain of fire, like almost like lava spilling off of these pretty like wires. It's just stunning to watch, and we had hours and hours and hours of that. And yes, it's absolutely driven by gravity. It's not the only thing. Obviously, we have magnetic fields and electric fields and things like that are causing, that are you know, creating havoc as well. But it is extremely difficult for us to get a good handle on all of these competing processes. And that's one of the reasons why the NCAR simulation is really kind of leading us into the next generation of simulations, because it's the first, not the first step, but it's the next step in trying to incorporate more and more of these these dynamic processes, these disparate processes on the sun into a cohesive model. And the more often that we do that, the more realistic our simulations become. And it's just wonderful to see. So hopefully that answers that question. Tamitha, what are the best universities to graduate in plasma physicists like you? I think most are in the USA. No, there's a lot in Europe too. It depends upon what you really want to go into. Remember, space weather, space physics, heliospheric physics is a huge set of disciplines. You can go all the way from, you know, the just above the neutral atmosphere and in the ionosphere and stuff like that. University of Iowa is really good for that. For example, they do a lot of, as a matter of fact, they work very much with the coders that are creating the global models for space weather for the ionosphere. Very slow going, but they're trying. GAME is an example of one of them. So you can go into ionospheric physics, you can go into magnetospheric physics, and magnetospheric physics is all over the place. Obviously, I'll call out my own alma mater, UCLA, of course, is a great place for that. Then you can go into things like solar physics. Solar physics, anywhere you find an observatory, you're probably going to find something in solar physics. Now, there's a difference between going into solar physics and solar astronomy, because if you go into solar physics or heliospheric physics that's looking at our sun and space weather, you're going to go into a different arena than if you were to go into solar astronomy. You go straight into solar astronomy, then you might be lured away and into something that takes you away from our solar system. And you really have to kind of be careful with the colleges there. For solar but space weather related stuff, UC Berkeley's fantastic. UCLA is okay. I don't know specifically anymore how much they're doing the stuff that I did, but I'm sure Chris Russell's still churning out grad students like crazy. He was my thesis advisor. But there are tons of really good places in Europe, Belgium. Talk to Chris Mostel. He does what I do, and he would probably give you another really good idea of where some good solar and space physics, space weather type universities are. If you were looking in, like, let's say Australia, Brett Carter is a person that you'd want to get in touch with if you wanted to do ionospheric physics, for example. There's just so many that really what you need to decide first is what discipline do you think you might really want to get involved in, because it's kind of hard to do all of it, especially at a PhD level. You'd have to get like 10 different PhDs. Obviously I would be thinking that's crazy. And I try to cover as many bases as I can, but I cover it at such a much more simplistic level. I don't even pretend to be an expert in ionospheric physics, for example, or magnetospheric physics. I just couldn't. There's just too much to know. So that would probably be a good place to start. You could also maybe work with a professor or do studies where you're kind of doing a little, maybe a senior thesis or something as an undergraduate that would allow you to dabble in certain areas in space weather and see what part really fits you, what really kind of, blows your skirt up, so to speak, and then dive into that as a graduate program. But, that's something we can talk about more offline. Okay, let's see. Do you know where the Parker-Strobe deal, or whatever they call that latest mission, do I know where it is? Yeah, it's close to the sun right now. It's doing fantastic. Some of the data, they're not releasing a lot of the data yet, only because they got to make sure it's cleaned, and they also have to be very careful because of the way the data is being collected, because this mission is so unlike any other. The way it's moving through the solar wind is so incredibly different. It's so much faster. It's also co-rotating with the sun in certain ways. They've just got to be so careful with how they're looking at the data and how they're collecting the data. And right now they're doing a lot of sanity checks to make sure they're not fooling themselves into thinking that the data is one way when in actuality it's telling them something else. A lot of things that you have to do with this data when you get it straight from the instrument is actually do a lot of math, because the raw data that you get doesn't tell you what you see when you see the data like published to NASA or published in a website or something. You actually have to do moments and do distributions and then deal with those distributions and make sure you have the right, you're doing the right integrals, you have the right distribution function. There's all sorts of things that you have to do to convolve, devolve, deconvolve, and all these other things with the data. And if you have the wrong assumptions, you can make mistakes and the data will look totally different. So that's what they're doing right now, and that's why they're taking time. Plus the fact that they can't get all the data down yet. There's only certain windows during which they can get the data down. And as of just the beginning of this year, when I was at the AMS and talked to Noir, the project scientist for Parker Solar Probe, he said that they don't even have a lot of the data down yet. It's still stored in the system. Because right now their main focus is making sure they get all the burns, all the thruster adjustments done properly. Because if they don't do these thrusters, at the right time with the right boost and the right this, right, delta V, all this other kind of stuff that all the jargon that they use, then you don't have a mission, or your mission is severely shortened. So that's the critical part. So they're not doing anything to jeopardize any of that. So they're backing off on pulling the data down from the recorder because they want to make sure that they get everything just perfect when it comes to the trajectory of the spacecraft right now, because it's so incredibly critical. Hopefully that answers that. Okay. Thank you, Hotness. Oh, that's sweet. Need to go to EMS work call. Oh, well, thank you. I appreciate you hanging on here. My God, there's always people who are a little strange. The Earth is flat with a dome covering it. Could asteroids striking the sun trigger or lead to CME genesis? It sure looks like it, doesn't it? No. I'm not even sure the sun even recognizes that these asteroids hit anything. Parker Solar Probe, if there's a comet that hits something, they're going to have eyes on, because at some small level, some local, level, sure, I bet you it does. Could it cause something as big as a CME? Probably not. Not unless the CME was about to go anyway, and the comet hit just right, because they're so, they're so small, and they get burned up so high in the solar atmosphere, and most of what we think are the dominating processes of a CME eruption and flare, reconnection and all of that stuff, that occurs so far down, at such low altitude, that really the comet coming in, it's kind of like when a meteorite, meteor comes into our atmosphere. How many of them even end up making it to the ground? We say, oh, there's a shooting star. Yeah, sure. Do any of them ever hit the ground? Well, very few. That's because they burn up in our atmosphere. Well, the same thing's going to happen with the sun too. And so a lot of these, they're so small, and the sun's corona's, a dangerous enough area that these things, these comets, even just with the solar radiation itself, just burn up to nothing long before they could penetrate deeply enough into the solar atmosphere to cause issues. But maybe at a local level, if it's large enough, anything is possible. But I just wouldn't count on it. Okay, let's see. You often talk about regions moving into the Earth strike zone as opposed to just the Earth-facing side. Where is the Earth strike zone? That's an excellent question. The Earth strike zone actually is slightly different for different structures. For example, when you have a coronal hole, the Earth strike zone for the fast wind that's going to be coming at the Earth is really close to the west limb. It's not even in the center of the Earth. When you see a coronal hole that's just crossing, let's say, this what we call the central meridian of the sun relative to the Earth-Sun line, that fast wind hasn't hit us yet. As a matter of fact, it has to rotate even further over for that to be an issue. And the reason for that is because what we call the Parker spiral. The sun, as it's rotating, if you were to think of a spiraling sprinkler head, and it shoots out water And if you look at it from above, it kind of makes like what looks like a pinwheel, right? You have this little pinwheel kind of effect where you've got the center of it, and then you've got these radiating spokes that are kind of bent and spin like this. And really, it's the same kind of thing happening on the sun. Because the sun is spinning, when it spits out something, that doesn't necessarily reach you just straight. I mean, the parcel goes straight out, but by the time that wind actually hits you, if it's a blast of fast wind, by the time that wind actually hits you, the source region has rotated even further out, or further off to the side. So the source region that actually hit through something that finally hits you, that source region is clear over here now. It's no longer facing this way. And it's the same thing with that water. With the sprinkler, by the time that the sprinkler fires something at you, it keeps rotating. And so by the time that thing actually hits you, it's now facing this direction, even though you're getting hit by something there. So that's really what the same thing with the coronal holes. We wait till they rotate over what we call the Earth strike zone, and that's what we know pretty much from the Parker spiral angle when something that it fired earlier has actually made it to Earth. It's a simpler way of getting people to look at the sun and say, okay, one view of the sun, one snapshot of the sun will give me an idea as to when I can expect weather from it. Is it perfect? No, it's not. And why the Earth strike zone is different for, let's say, a coronal mass ejection, where I can say, okay, if a coronal mass ejection is launched right when it was launched at central meridian, is because that source region now is gone. It's just a transient thing. It doesn't stay on the sun. So as the sun continues to rotate, you don't keep watching that source region where the CME came from. You know that it was launched right there, and so it will come at you. So it ends up being kind of a cheating way of having a single snapshot on the sun. It's not supposed to tell you kind of the physics of what's going on, but it's a cheating way to look at the sun, see where something is occurring on the sun at that moment, and say, okay, now that you should expect space weather from it at this time. You know, it's part and parcel. If I try to talk about the actual physics of it, then we have to actually get into, well, the source region really isn't what you're experiencing now, isn't what's actually coming out of the sun right now. It's what came out of the sun when the sun was rotated back, and it gets a little bit more complicated. And so I just kind of just punt and say, no, Earth strike zone, there you go. When it looks like this, then you're probably going to get that fast wind from the coronal hole. But when something is launched like a CME, it can launch at central meridian and it will hit you, and have a better chance of hitting you. And yeah, I'm just using the Earth strike zone in two different ways for two different, fundamentally different concepts. And yeah, I realize that can be slightly confusing if you're trying to relate it to the physics, and I apologize for that. But it still seems like the easiest way to get people to understand when the space weather is going to hit. So I keep using it, and I hope that doesn't upset anybody too much. But you know, I'll see if I can find a better way of talking about it. Let's see. Okay, poll on the next solar max. There's a lot of scaremongers saying we're in for a mini ice age. Oh boy, that's so hard to talk about. The only reason why is because we're still working on that. You know, we've had in the human time scale, especially for the space age, we've had so little experience and so little instrumentation that can reach so far back. When we look at the sun's time scale, it's so incredibly long. And when we look back at modern instrumentation, it's such a small window of this incredibly long time scale of the sun that when we see a few wiggles here and there on our time scale, we think, oh, the sun did that just 30 years ago. Oh God, it's going to do it again. You know, or 100 years ago, the sun did this. Oh, we're going for another one of those. And it's like, well, you know, that's a rush to judgment, you have to admit, because really in the end, there have been a lot of minimums that the sun has had. You know, people talk about the Maunder minimum, but did you know there were many minimums before that? The Spore minimum, for example, which was much deeper. We have evidence of that from ice cores. and carbon dating and all sorts of other ways that we are able to look at cosmic ray flux and cosmic ray penetration over, hundreds and thousands of years, that give us an idea of what the solar activity was long before we had modern instrumentation. So to say that we're headed for another Maunder minimum and sunspots are going to go away and we're going to have another ice age and all that kind of stuff is, I don't think it's responsible. I think we can safely say that we're in what we're considering another grand solar minima. But what that means just means that solar activity is kind of waning a little bit. We just came out of a grand solar maximum. What does that mean? Well, it means the biggest events were maybe a little bit bigger than they'd normally be over, essentially what has been the current space age. And now we're going into a grand solar minimum, which means, well, the activity, maybe the events overall could be a little bit smaller than we expect. Except for some interesting research that we've seen and some interesting insights that we've gotten somewhat recently about the fact that these small activity cycles may be happening when the hemispheric pole, the magnetic field of the two poles are out of phase. And when that happens, that's what causes, there's a lot of cancellation, and that causes overall the activity to go down, but it causes the complexity of the magnetic field to go up. And that is bad juju when it comes to coronal mass ejections and active regions, because now you get these really complicated looking active regions, and that's the ones that let the big Carrington events out. So overall activity is going down, but now the big scary monster events may have a higher probability of occurring. Do we know this for sure? No, but we're sure kind of scratching our heads a little bit, because just in this last solar cycle, even though as weak as it's been, we've seen 3 Carrington class or near Carrington class events. And one of us tagged us. One of us was from that, remember that tweet from Ariake showing that huge EIT wave? And I told you about the gun firing this way and yet it still hit us? That was a Carrington class event. And that thing should not have been able to hit us when you're pointing a gun this way. I mean, it just blows your mind. And it caused a G1 level storm. So it even caused we even reached storm levels from that thing, even just being clipped by it. And then, of course, the famous one in 2012. And then there was one more that was Carrington class or near Carrington class. Nonetheless, very, very extreme events. And a lot of us kind of go, well, why is that happening for, these low activity cycles? And then there's a handful of scientists that say, aha, we have the answer. It's because these hemispheres are off and you get hemispheric band compression that create these very ugly sunspot regions like, what was it, 2376, I believe, the one that we had back in September of 2017. And so, yeah, okay, we may be going into a grand minimum, but that doesn't mean we're scot-free. It means, we could get, a little bit less activity, but then we get the big whoppers that hit us. So, that's the one thing that we're learning about space weather, is that there's never quiet space weather. There's no benign time for space weather. Even with the lower activity cycles now, with the sun kind of quieting down, we're getting cosmic ray penetration in our upper atmosphere like we've never seen. And not in the space age anyway, which is bad because we've got all these polar flights and routes with the FAA now, at least in America, and in the all the airlines worldwide. They're getting far more cosmic ray penetration and radiation doses than they ever used to. So, that becomes an issue. So again, the idea of space weather being benign or the sun going to sleep, that causes its own issues. And it still means that the space weather, at least from our point of view, the space weather is pretty busy. So hopefully that answers that question. Okay, let's see what's next. Anything else, guys? I've talked your ears off, I think. Are we headed towards a Maunder minimum? Yeah, I just talked about that. Hopefully, did I get everything? I'm going to check on... oh, really? Are there conditions awful on HF right now? I thought they were doing a little bit better because of this new region. I would like to know if the sun is actually a gas, or is it graphite with some sort of reaction in the center? I can't see it not being solid. Oh, Lordy, that's a question for, that's definitely a question for a solar physicist. I don't think it's solid. It may have, the radiative core may have something like that in there. I'm not sure exactly what all the theories are about the core. A lot of it in the core is hard to see in it because it's opaque to a lot of the instruments that we have. So I think there's a lot of unanswered questions regarding that. Remember, what did they say? Something like it takes 100,000 years for light to escape the radiative boundary of the core because it's just all the electrons are stripped off. There's so much energy going on. Everything is bouncing around and hitting one another, and nothing can escape. It's just too hard to get out light, even photons. I think it's something like that. And I don't pretend to study any of that stuff, so I am not the right person to ask that question. But I might, I could look it up and see if it makes, if I can find any really solid answers on that. But I'm not sure I will. I'm not sure I'll find them. Okay, I still don't see anything on Patreon. I wonder if nobody's commenting on Patreon or if my thing is not updating. I had that one other time. Oh, here's some. Okay, hold on. Any reasoning for the extra high electron flux today? Are we seeing high electron flux today from in the satellite, in the geosynchronous, like the Earth environment, or are we talking about electron flux from the upper atmosphere? The upper atmosphere may be getting ionized a bit more because of the region, the new region that has been flaring for us. Let's see. Let me go really fast to space weather. Are we getting any new data here? Is that it? Oh, come on, get off. Let me reload. It doesn't look like we're seeing any more. Are we reloading? Maybe. It's going to try. Looks like my internet may be slow right now. I don't think we've had a big flare, have we? Not since. No, we haven't had any new flares. So we do have that region. It's still boosting our X-ray flux to essentially the B floor. So by proxy, the solar flux is going to be a bit higher. So we're probably going to be getting a bit more ionization in the upper atmosphere. So that's why I'm surprised to hear that HF radio is not doing too well. It may be during some of these the noise that you can get from these active regions. It may be making enough noise that you're getting some your noise floor is raised. But it should have actually helped radiation propagation today on the day side. So I'm not sure, and we don't have a strong magnetic field. I mean, there's no there's no solar storm going on right now, so we should be pretty quiet when it comes to most of that stuff. So I'm kind of surprised to hear that we were having issues. Anyway, that's all I've got on Patreon. So any other questions, guys? If not, I will call it a day. Do CMEs and/or flares affect the planet equally, or does the sun-facing side of the planet only get affected? CMEs are completely global. Okay, CMEs are completely global. So when a CME hits Earth and causes a solar storm, or a geomagnetic storm, as we call it from Earth, that is a global phenomenon. Most likely, more often than not, you're going to see all of the effects, most of the effects anyway, at nighttime. And that's because of how the Earth's magnetic shield reconfigures itself. It configures itself mainly on the tail side of the Earth, and because you've got the solar wind coming from the sun and it blows at the Earth's magnetic shield, it kind of makes the magnetic shield stretch out in the back and make it like a big comet tail. And so all the reconfiguration typically happens around the backside, and that is the night side of Earth. So for most purposes, you will have those issues from a CME hitting Earth. You'll have most of those effects occur at night, and that's mainly just because of how the Earth's magnetic field is configured. With solar flares, it's the opposite. If you can see the sun, it can see you, which means that when the sun screams, if you can see the sun, you can hear it screaming. If you're on the backside of Earth, though, and it's nighttime, you're not going to get affected. So solar flares don't affect HF radio at night. You won't get all the pops and whistles. You won't get all that kind of stuff. And as a matter of fact, that's during the recent solar flares back in 2017 when we had Irma hitting Puerto Rico. that was the advice that I gave the HF radio, the emergency responders. I said, look, I said, daytime, you're probably going to have a horrible time trying to communicate on the bands, but just wait till night. I said, because we've got a couple days before the next solar storm hits, and for at least for that period of time, you're going to be better at night. I said, but then when the solar storm hits at night, or hits in a few days, then the night side's not going to be much better. So that's the interesting thing about space weather, is that depending upon the phenomena that you're dealing with, that will dictate what part of the Earth and how dramatically you will be affected. So hopefully that answers that question a little bit. Let's see. Are planets smaller than quite a few sunspots? Asteroids are so much smaller. That is true. What does a CMA on the backside of the sun cause a wave or fast wind to hit Earth? A CMA, what is a CMA? I have no idea what you mean. A CMA. Okay. Cool. So nighttime is better on HF. Nighttime is better on HF. No, not always. Nighttime will be better on HF when there are big solar flares. Now, I would think, because we're only getting small C-class flares, HF should be fine. It might be a little bit more noisy during the daytime, but HF should be doing pretty well right now. When HF is better, or when HF is worse at night, is when we have a solar storm. So when we have something like a CME hitting, daytime HF radio is, using HF or using the bands during the daytime is probably a better bet. So hopefully I got that clear for you. I know it's kind of tricky, and one of these days I'm going to put together a comprehensive emergency response or emergency responder space weather mitigation talk or something like that, that just specifically talks about HF radio, specifically talks about what you should be doing, and what local times you need to be considering, working the bands when it comes to different space weather phenomena. We really, a lot of times with HF radio, everybody gives me the UTC time. And I'm like, well, I don't really care about UTC. What I really care about is your local time. And in actuality, what I really care about is your magnetic local time, because everything, when it comes to space weather, is organized by the Earth's magnetic field. And so that shield looks different at different local times. And what type of space weather you're dealing with is very dependent upon that. So that, to me, is actually more critical than knowing what the UTC is, because that doesn't tell me where on the globe you are. And so that's one of the things I want to kind of start calibrating emergency responders to think more like, is to think in terms of their of the Earth's magnetic shield, and think about their location in it relative to what space weather phenomena might be occurring, and so where their safe zones are for these different phenomena. But I'm still kind of putting that together in my head, and but I'll let you guys know when I'm close to it, and hopefully that'll make things a little bit easier for you. Okay. Thanks. This is the best YouTube channel ever. Oh, that's so sweet. Thanks, guys. That makes me feel good, especially when I've got you can hear my voice is kind of dying on me. So, okay. August 4th, 1972 and 1859 have similar planetary alignments, 7 planets opposite Earth seen with the sun. It's so interesting when people talk about that. I don't think that's an area in which where the space weather and astronomy have collided yet. There's a few people, a few scientists who have talked about this, about the tidal pulls of large celestial objects, and how that tidal, the gravitational pull when things are aligned could actually cause, some level of disruption in the sun, in the solar interior. And I just, I marvel at that, because it's such an interesting question. And there's got to be ways that we can answer that quantitatively in a fashion that is robust. Because I don't think anybody has really seriously gone after something like that, if for no other reason than simply because there's lower hanging fruit, as we call it, as scientists call it, There are a lot easier answers to get by doing things that take less time. When you have questions like that that are so off the beaten path, now you got to sit there and go, okay, I got to get this data set together with that one, and then this one needs to be cleaned of this stuff, and how am I going to talk to that group over there because they've got the data I need, but I don't even know anybody in that group. And you just start thinking of all the logistics before you even start the study. And most of the time that's enough to make scientists go, ugh, forget it, it's too hard. So they just blow it off and say, I know how to work this problem, let me just work this problem. But some of these other problems are just so fascinating, and I don't see any reason why somebody, a scientist somewhere, especially a graduate student, that's probably not how it's going to happen, is as some of these fields get to be closer together, and space weather gets to be a much more solidified field in its own right, you're going to have weather people, meteorologists, who are going to want to make more of the connections between the Sun-Earth system. And you're going, from the neutral atmosphere coupled up to the charged atmosphere, the charged part of our atmosphere, the ionosphere and beyond. And you're going to want to get astronomers who are looking at planetary and gravitational pull and stuff like that, and tidal forces, and look at that and couple that with space weather, But our field is just so young yet that I don't think it's gotten enough, I don't want to say legitimacy, because that's so wrong, but it hasn't gotten enough clout, enough prestige yet to really bump up that threshold and pop through that interest level. But that's what this is all about. I mean, that's why we're doing this, and that's why you ask questions like that. Who asked that question? I missed where you were asking that question, but I apologize for not catching your name. But yeah, ask these questions, absolutely, because eventually it's going to rise above the level, above the pain threshold of actually doing it, and someone will actually sit down and do it. I mean, it's the same way how dark matter was discovered, right? You had an astronomer, a female astronomer, who was kind of shoved off to the fringe, and she was only part-time, and everybody else was taking all the cool stuff. So she started studying stuff that, nobody else wanted to, simply because it was too hard, or it was not interesting, or it just didn't seem like there was anything, worthwhile in it. And lo and behold, she ends up studying, she ends up revealing dark matter existing. And that's how some of the most amazing breakthroughs happen. So, so that's what I'm hoping for this field. I really am hoping that we are going to start opening these huge doors into meteorology, and opening these huge doors into the links with astronomy. But we're not going to be doing it in such a fashion that everybody thinks that we're just waving a bunch of crystals around and reading everybody's horoscopes. That, and I'm not like Carl Sagan. I love him to death, but I am not someone who bashes astrology. I don't bash it at all. I think it's very intriguing, and I think there's a lot of really kind of cool mystical stuff that actually works with astrology that I just scratch my head and go, how the hell is that true? But it's true. So, I just kind of look at that stuff and just awe, wonder, and smile at the whole thing. But I do know that as scientists, you have to be able to have something that is a rigorous attempt. And so we have to be a lot more quantitative and unfortunately boring when we go about some of these studies. It has to be much more rigorous, and has to be much more careful and conservative, and we can make the quantum leaps in our mind, but then on paper, when we write it down and publish it, it has to be so well vetted before it's really accepted. And even then it's not accepted. Look at Parker. Look at Eugene Parker's theory of the solar wind. He was laughed at, absolutely laughed at. And now everybody prays at the altar of Eugene Parker. This is just the way science works, and there's no getting around it. So, the critical part, of course, is asking these questions and not letting them go. But then understanding and being patient with the field as it struggles with what it thinks is a worthy pursuit and what doesn't. It just is what it is. Okay. All right, guys. I'm only the electric universe model. Well, yeah, the electric universe, the I think the rub with the electric universe is that they just basically tell everybody that magnetic fields are irrelevant, and basically tell us that magnetic reconnection means nothing, and that Maxwell's laws that have been well accepted for centuries and have been well proven, that those laws are fundamentally stupid. If that's how you start a dialogue, then yeah, every scientist in the world who studies electromagnetism is going to shut you down. It's that simple. That's just not how you start dialogues. You also don't start dialogues with scientists by telling them that they work for Big Brother and are hiding things. That's not really a positive discourse either. So I think the electric universe folk, in general, I'm sure there are many who are wonderful, but in general, I think a lot of the electric universe folk have kind of gotten off on the wrong foot, and have shut down what scientists consider, respectable discourse, and that's going to be a problem for a while, and I don't know how to fix it. I'm not here to fix it. I'm just here to make space weather more accessible to anybody who wants it. So we'll see. I have high hopes that the fields will reconcile eventually, but right now, I'm not sure how much headway we're making in one way or another. But keep trying. We keep trying. Stellarium is a good as a data program. I have no idea. Okay. All right, guys. Is she a full professor? No, I'm not a full professor because I don't work at a university. Full professors work at a university. Do I have a PhD in space plasma physics? Yes. If I wanted to become a full professor, could I? Yes, I could. I have all the credentials, but I didn't want to do. I didn't want to become a professor and have graduate students. To be honest, I'd rather teach you guys. I'd rather teach. I'd rather try to bring fields together, like meteorology. I had way too many of my colleagues in ionospheric physics say that our technology is so far outpacing our ability to understand the things that affect it that what's going to happen is people are going to die. And we need to figure out how to push policy in such a fashion that it gets space weather more connected to meteorology. And until we can do that, space policy is going to fall far behind things like space tourism. And people are going to get sick from radiation poisoning, and they're not going to know why. Or we're going to have catastrophic failures due to people not being able to receive their GPS. The satellites will be working just fine, no problem there, but everybody who relies on them down here can't use them because we've got, a solar flare, series of events that is making it impossible to receive GPS, and nobody understands why, and we have catastrophic failures due to that. People die, drones suddenly become deadly weapons. And nobody understands what happened. Their drones are just now out of control. Or we have solar particle events that are huge and so many polar flights with the airlines that people are getting, cancer, and they're getting cataracts, and they're getting all these sicknesses that they don't understand that are really due to just simply high radiation doses due to space weather. These are the types of problems I want to fix. And I can't fix that by training graduate students who are just simply going to go into academia and hold all of their information only for a scientific few. It's just not what I want to do. We need those people, absolutely. I have many colleagues who are full professors, and they're churning out grad students, and I'm loving it because the work that they do is so essential. But that doesn't mean that I'm going to become a professor and do that too. But do I have the credentials to become a full professor? Absolutely. As a matter of fact, I'm going to become an adjunct professor at Millersville University so that I can create the certification curriculum through Millersville for space weather. So for broadcast space weather, hopefully, to train meteorologists and others who will hopefully be consulting with all these agencies and helping bring space weather into the public eye, into the public arena where it needs to be, so we can ultimately save lives. So that's where I am. Okay, so 3+ hours. Yes, I think it's time for me to get out of here, guys. Did you ever meet Barb Thompson in charge of SOHO? Oh, did you go to school together? Yes, I love Barbara. She's so nice. She and I are very good friends. I have her cell phone number, as a matter of fact. I was so bummed because she was supposed to be at the AMS this year, and of course, as you know, she's not able to. So I missed her this year. I was so upset because I haven't gone to the AGU over the past 2 years. So AMS was the only place I was able to see her for our once a year little get together. Yeah, we typically go and eat dinner or breakfast together or something like that, and generally commiserate about the state of things. So I absolutely miss her. She is one of the most charismatic scientists I've ever known, and she just thinking about her, she's an inspiration every day. So it's nice to know someone else knows her, and hopefully, you know, reveres her as much as I do. Yeah, I love Barbara. Okay, time to close, Tamitha. Yes, yes, yes. Okay, the moon is an illusion. That's a beautiful. I think I'll end with that. Please don't stop doing the space whether you have found your calling. Oh, thank you. Oh, that's so sweet for you to say. And yeah, as long as you guys are still here, you're learning, you're listening, you're helping me know where to go next. You know, I follow you absolutely, because you guys are the heart and soul of this whole project. And I'm just so grateful. You know, I think this community is something that that is growing by leaps and bounds. And as long as we stay true to each other, then I think we're all going to go in the right direction, and that we will change this world. We will bring space weather into our living rooms, and we will be able to absolutely change the paradigm of how we look at the universe and how we look at just our everyday lives. So ultimately, with your help, yes, I hope that is my calling, and I'll keep trying. I'll keep working it. Okay, guys. I am hoarse, you are beautiful, and hopefully you've enjoyed this mini course. And stay tuned for the next one, because I'll either go straight into solar flares on the sun, and it'll be a counterpart to this, or I'll go into the solar wind aspect of coronal mass ejections, which are called interplanetary coronal mass ejections, or ICMEs. So one or the other, I have to talk to everybody on Patreon who is at the mini course tier. They are steering me, and it will be they ultimately who decide which direction we go next. But you guys have been great. Thanks for all the wonderful questions, and I will see you very soon. Okay, bye.